Hello and welcome to Pluralsight. My name is Pankaj Jain and welcome to this module on Oracle PL SQL, Transactions, Dynamic SQL and Debugging. In this course, we start off discussing transactions in Oracle PL SQL. We will take a high-level overview of how transaction management occurs in Oracle database. Then, we will talk in depth about commits, rollbacks, save points, naming transactions, initiating read-only transactions, etc., and other concepts which should provide you a firm grip on transaction management in PL SQL in order to write code which is accurate and performs as expected. Autonomous transaction is a very neat feature which was introduced in Oracle version 8i. It allows you to initiate an independent transaction from within another transaction. This enables you to do with extreme ease and grace activities like logging, auditing, usage monitoring, and several other use cases which would have otherwise required a lot of complex coding. Dynamic SQL lets you write SQL which is determined at runtime versus compile time. You can write extremely flexible code and avoid a lot of redundancy using Dynamic SQL. Native Dynamic SQL is one way of writing Dynamic SQL. It is very simple to use and understand and supports both Oracle supplied data types as well as user-defined data types. We will see how to write single row and multi-row selects, DDL, DML, and session control statements using native Dynamic SQL. We will also see how to execute anonymous blocks and stored subprograms using it. DBMS SQL is a built-in package in Oracle which provides us an alternate way of writing Dynamic SQL. This has been around from very early versions of Oracle and has some unique capabilities of executing Dynamic SQL where the number of columns in the select statement are unknown or the number of bind variables in a SQL statement are unknown. We will see how to execute anonymous blocks, DDL, DML statements, etc. using it. Finally, we will talk about how we can effectively debug our code when it is not giving us the expected results or is erroring out. We spoke about DBMS output and DBMS utility packages in the Oracle PL SQL Fundamentals Part 1 course. We will briefly touch upon them over here. We will build on our discussion of SQL Developer Debugger from the Part 1 course and explore the capabilities when debugging stored program units. We will see how to observe the data values and execution flow, as well as how to quickly reach the offending lines of code in a subprogram even when it is buried several layers down in the call stack. This course is a continuation of the Oracle PL SQL Fundamentals Part 1 and Part 2 course on Pluralsight and builds on the concepts we learned in those courses. So if you have not checked out those courses yet, I would highly recommend you to do so. In the Part 1 course, we cover some of the basic concepts and programming constructs like anonymous blocks, PL SQL data types, conditional executions, loops, cursors, exceptions, etc. In the Part 2 course, we talked extensively about named program units like stored procedures, functions, and packages, which help encapsulate business logic pre-compiled and stored in the database. These concepts will come into play as we discuss transactions, Dynamic SQL, and debugging stored program units in this course. So one of the prerequisites to be more effective with this course is to take the Oracle PL SQL Fundamentals Part 1 and Part 2 course, or otherwise you should have equivalent programming knowledge to get the most out of this course. So who would be the audience for this course? This course is for Oracle programmers having a fair experience and a good understanding of the basic concepts of PL SQL programming. For Oracle programmers who want to learn in detail concepts around transactions, write Dynamic SQL, and know how to effectively debug PL SQL code in order to understand the execution flow and provide bug fixes quickly. Concepts essential to become proficient in Oracle PL SQL programming and harness its power. This course would also be useful for web programmers who would like to gain the optimization and efficiency of executing the database and SQL-intensive business logic in the database layer versus web layer, thus preventing multiple round trips to the database and network latency. And this course would also be useful to other programmers who have been following along the Oracle PL SQL Fundamentals Part 1 and Part 2 courses and want to expand their knowledge of Oracle PL SQL programming to be more effective with it. In this course, we will be talking about PL/SQL programming constructs which should work with most Oracle database versions. However, it is always recommended to use the latest version in order to take advantage of the optimizations and features which come in with each new version. For the demos, I would be using Oracle Express Edition. It is an entry-level, small footprint database free to develop, deploy, and distribute on. And it would be sufficient to practice the concepts we would talk in this course. For the tools, I would be using Oracle SQL Developer exclusively. It is a free IDE or development environment which you can download from Oracle's website. It has IntelliSense, Code Explorer, and several other useful features to make writing and debugging PL/SQL very easy and efficient. SQL Plus is a command line utility which you can install on the client machine to communicate with the database. You can use it for running scripts against the database. A lot of the examples we will talk in this course can be run using SQL Plus. However, if you have access to and are more familiar to other IDEs like Toad and SQL Navigator, just to name a few, feel free to use them. I will be using SQL Developer exclusively for running the demos in this course and use its easy to use and powerful debugger when we talk about debugging in the last module of this course. Hi, welcome to Pluralsight. My name is Pankaj Jain and welcome to this module on transaction management in PL/SQL. We all are very familiar with the concept of transactions in our day-to-day lives. We do transaction at checkout counters in stores where we pay money and buy some goods, or at an ATM counter where we swipe our debit card to debit our bank account and receive some cash in return. Transactions are an integral part of a database management system and one of the ways a database differentiates itself from a file management system. Oracle Database has a very robust and powerful transaction management framework, and it provides us with a lot of transaction control statements to have greater control over our transactions. It is very important to understand the concepts of transaction management in PL/SQL in order to write code which is accurate and provides expected results. In this module, we will first try and understand transaction management in Oracle at a high level. Knowing how things work behind the scenes always helps in understanding the concept better. We will then talk about commits, rollbacks, and save points, which are transaction control statements which enable us to set boundaries for our transactions and have more control over them. We will see how we can name our transactions to better monitor them, initiate read-only transactions for point-in-time reports, and briefly talk about logs. Let us take a closer look at this important concept. Oracle Database supports ACID properties for the transaction. The A in ACID stands for the atomicity of a transaction. It means it is either all or nothing. Either everything goes or nothing goes through. It supports atomicity in all possible situations, even during crashes or power failures. C stands for consistency, which ensures that a transaction will bring the database from one consistent state to another. I stands for isolation, which means that concurrent transactions would result in the same final state as if the transactions were executed one after another. And D stands for durability, which means that once the transaction is committed, it will be durable or will be permanent even if there is a system crash or power failure. The database will have recovery mechanisms in place to ensure that the commit is applied. So, what is a transaction? A transaction is a logical atomic unit of work comprising of one or more SQL statements. All these statements either are applied together as one or not applied at all. The transaction begins with the issuance of a DML statement like select, insert, update, or delete statements. They also begin with the issuance of a DDL statement like create table. Set transaction statement through which you can give your own name to a transaction or specify transaction mode like read-only, etc., also can start a transaction. The transaction ends when you issue a commit, which makes changes permanent, or rollback, which undoes the changes. We will talk more about them shortly. A DDL statement also implicitly issues a commit, thus ending the transaction. You should remember this, as sometimes you may accidentally commit a transaction even though when you don't intend to do so by issuing a DDL statement in your transaction. A transaction also ends when the session ends, either when the user exits normally or when the session is terminated abnormally. We will talk about the implications of these situations shortly. Let us take a high-level overview of what happens in a transaction. Let us say we have a transaction started which has a bunch of DML statements. When the transaction starts, Oracle takes a snapshot of data to capture the before image and keeps the undo information in an undo table space. This can be useful to bring the data back to the old state if the transaction is rolled back or is undone. As the transaction proceeds, changes made are recorded in memory in an online redo log buffer. The data blocks worked upon during the transaction are kept in the data buffer cache, and any changes made to the data is also reflected by changing the data in the data buffer cache. Say an error occurs and we decide to roll back the changes. Rollback is to undo the changes made. Then the database makes use of the undo information it had stored earlier to bring the database back to the state before the transaction started. However, say if everything goes well, then we decide to commit. In that case, the database will write the online redo buffers to the redo log file on disk. This would be useful for recovering the database in case of crashes. The changes in the data buffer cache will make their way to the data files on disk. This can happen anytime before or after the commit. Oracle tries to optimize the write to the database files by batching them up in order to reduce network IOs, locks, and latency. Since Oracle has the redo information in redo logs, it can use it for recovery in case the database crashes before it gets a chance to propagate the data buffer cache changes to the data files. Let us take a quick look at an example to understand transactions. Let us say we have a procedure, process order, which is used to place orders. It takes in P account ID, the account ID placing the order of type accounts.accountId %type. P item ID is the item for which the order is being placed of type items.itemId %type, and P item value is the value of the item. The transaction begins with the first DML statement, which is an update to the accounts table, reducing the account balance by the item value for the past account ID. Next, we insert an order into the orders table, inserting order ID as the next value from the sequence order sequence.nextVal and P item ID and P account ID. If everything goes well, we commit, which ends the transaction, making the changes permanent in the database. However, if there is an error, say during the insert statement, then an error would be raised. Inside the exception block, we have a when others handler where we print the dbms utility.format error stack and dbms utility.format error backtrace using dbms output statements. Then we issue the rollback, which will end the transaction and will also undo the changes made by the transaction. Lastly, we issue a raise to raise the exception to the calling client. We want both the legs of the transaction to either go together or not go at all. So the use of the transaction control statements like commit helps us draw the boundaries of our transaction, and rollback ensures that if there is an error, the entire transaction is rolled back. We will talk about commit and rollback in more detail shortly. Before that, let us take a look at how to name a transaction. If you want, you can give your transaction a name. You do so using the setTransaction command. The syntax is setTransaction name followed by the transaction name. So a transaction name is a user-defined name you can give to identify your transaction. It has to be the first statement of a transaction, and if there are DML statements before it, Oracle would require you to either commit or roll back those before you can issue a set transaction statement. It is of course optional to name your transaction. Its main use is to monitor long-running transactions, as a DBA can identify the transaction by its name using Oracle Enterprise Manager or data dictionary tables. The database also inserts the transaction name to the transaction audit redo record, which is useful for searching the transaction in a log using a utility like logminer. $transaction is the table which a DBA can query to monitor the status of a long-running transaction. This table has the transaction name, status, consistent read gets, physical I/O, undo records held, and a lot of other useful information about a running transaction. It shows information only for active transactions, and as soon as the transaction is over, the row disappears from the table for that transaction. So for instance, here is the same procedure, and I'm just showing partial code over here. We can put the set transaction name place order in the beginning of our procedure to identify the transaction. We can then run the procedure as exec process order, passing in account ID 1, item ID 2 with an item value of 500. While this procedure is running, a DBA can issue a query like select name status from $transaction to identify the transaction from the transactions table, and then further issue queries to monitor the resource usage. Of course, you can also see the transaction name when you issue DML statements in SQL Developer or SQL+. For instance, say a DBA user logs into SQL Developer and issues the set transaction statement setting the transaction name to my transaction, and then inserts into the demo.items table. Then after that, the DBA can issue select name status from $transaction to identify the transaction and further query to monitor the resource usage related to that transaction. Once the transaction is committed or rolled back, the transaction disappears from the transaction table. Using setTransaction command, you can also initiate a read-only transaction. The syntax is setTransaction read-only name with the transaction name. So where would you use that? Typically, when you want to read data using a snapshot of data from when the transaction started. In the typical transaction, a select statement would read data, which is the committed data at the point in time when the select statement started, and not the state of data when the transaction started. After the transaction started, say another session changes and commits some data. Somewhere later in our transaction, say we have a select statement which queries that same information. It will see the latest changes, committed data at that point of time, and not the data at the point of time the transaction started. But for some kind of reporting, say a month-end report job which starts at midnight, there might be a requirement that when the transaction starts, you just want to report based on the snapshot of data at the point in time when the transaction started. The read-only transactions might be useful in those cases. Oracle provides a multi-table, multi-query read-consistent view. It has to be the first statement of the transaction, and the read-only transaction ends when a commit or a rollback is issued. So in this code snippet, we initiate a read-only transaction by using the command setTransaction read-only current month order count. Then we issue a bunch of select statements to read the total count of orders for a customer for a current month. The commit at the end ends the transaction. Let us talk about commits in more detail. As we know already that commits make the changes in the transaction permanent. Online redo buffer information is written to the redo logs, and database files are also updated ultimately to reflect the changes. A system change number is generated. A system change number is a logical internal timestamp used by Oracle to keep track of the events and the order in which they occur. Every committed transaction gets an SCN number. All changes in the transaction get the same SCN number. So SCN 10 is an event which has occurred before SCN 11. This also helps Oracle during recovery process and marking and keeping track of what changes are on disk. You can observe the SCN number for an active transaction from the same $V transaction table. A transaction places locks on the rows it affects. A commit releases all the locks and frees all resources tied to that transaction. We have not talked about save points yet, but a commit also erases all save points set until that time. One thing to know about commits is that until a commit is issued, changes are not visible to other sessions. Uncommitted changes are only visible to the session making the changes. For instance, let us say in a session we issue an insert to the items table for item ID 3 with item name treadmill and item value of 400. So if we try and issue a select from the items table for item ID 3 in the same session and try and show the value of item name using DBMS output, it will print out treadmill as it can see the changes. However, let us say we have another session in SQL Developer. It doesn't matter if it is another session with the same user ID. If it tries to query the item name for item ID 3, the query will return back with nothing. However, after the transaction is committed, the same query in another session will be able to fetch the item name treadmill for item ID 3. Let us talk about DDL statements, as I think they fall in a special category. When you issue a DDL statement, it will first commit any outstanding changes and then would run as a transaction of its own. So here, with the update statement, the transaction begins. Then we issue a DDL statement, execute immediate drop table temp table. Notice the syntax execute immediate. This is the dynamic SQL syntax, which is the only way you can issue DDL inside PL SQL. We will talk about dynamic SQL in more detail in a later module, so do not worry too much about its syntax. Issuing the DDL statement will end the previous transaction by issuing an implicit commit. It will then also start a new transaction for the DDL statement. Once the DDL statement is executed, the transaction would end. When the insert statement is executed later on, it will start a new transaction, which will end with commit if everything goes fine, or with a rollback in case of an error. I just wanted to specially point out how DDL statements can affect an existing transaction by committing when you may not be intending to, something you should be aware of. Finally, say if you exit your session normally and there are outstanding changes which you have not committed or rolled back yet, tools like SQL Developer will prompt you with whether you want to commit or roll back the outstanding changes or abort the disconnect. In SQL Plus, the default behavior is to roll back. In SQL Developer, in the menu option under Tools, Preferences, Database, Object Preferences, you can set Auto Commit on, which will commit automatically after each DML statement. But I would not recommend doing that to avoid accidental commits. We have talked about the rollback statement a few times earlier. A rollback statement undoes all changes made by the transaction and brings the data to the state before the transaction. It ends the current transaction. All the locks and resources on the objects involved in the transaction are released, and it also erases any save points established in the transaction. We will talk about save points shortly. Let us take a look at the same procedure as before. The transaction begins with the update statement, and if everything is successful, ends with a commit. But in case there is an error, the execution will flow to the exception block where a rollback will be issued to revert the changes made by the transaction. So the rollback ensures that any errors reverts all changes in the transaction as a whole, and thus supports the atomicity aspect of an asset transaction. The error can be system generated, say in the case of an error during the insert, where the execution will flow automatically to the exception block, or it can be a user-defined exception, whereby using the raise statement, we make it flow to the exception block where we issue the rollback. Let me now talk about statement level atomicity. A SQL statement is an atomic unit of work. When you issue an update, it does the relevant updates and comes back. An insert would insert a row and come back. Each of these statements performs a unit of work. Then you tie the work done by these statements together in a transaction using a commit or a rollback. So if a SQL statement fails, it rolls back automatically the work done by that statement alone, but the work done by another statement before it would still stay. So if you have an update statement followed by an insert statement in a transaction, and the insert statement fails, it will only roll back the changes the insert statement was trying to make, but the work done by the update statement will still stay. All the side effects of this statement are also rolled back. So for instance, if that statement in turn calls a trigger to be executed, then the changes made by the trigger are also rolled back. So all changes made by that statement and the statements it invokes automatically are treated as a unit. This is called statement level atomicity. So if we take a look at the same procedure, say our update goes through successfully, but there is an error during the insert, in which case the execution flows to the exception block. Here if you were to issue a commit, the changes made by the update statement would be committed. This is an important concept to note so that you can avoid unexpected behavior due to commits, where you might think that since one of the statements failed, all the work done by the previous statements in the transaction are also rolled back automatically. Let us talk about some other rollback considerations. If the session ends abnormally, say due to a machine crash or power outage or whatever, Oracle will automatically roll back any uncommitted changes. A rollback transaction does not undo any package or session variable changes. Let us say we have a package account management with a global variable gdebit. So for instance, in this partial code, if after the successful update we set account management.gdebit to a value of y, and then say later there is an error in the insert statement which causes the flow to go to the exception block where we issue the rollback statement. But this would not roll back the changes to the package variable as evident by the DBMS output statement after the rollback. So you need to keep track of changes to package variables and reset them manually in the rollback section. In this demo, we will take a look at a transaction. We will see the effects of rollbacks and commits and understand statement level atomicity. First, let us create the setup tables. We have first the customers table, which has a customer ID, which is its primary key, customer name and customer location, both varchar2 columns. Then we have the accounts table having the account ID as the primary key, account customer ID linking the customer to the account, and account balance and the constraint account customer FK, which is a foreign key constraint linking account customer ID to the customer ID in the customers table. Then we have the items table where we have the items to be sold having the item ID, item name and item value. Next is the orders table, which will contain the orders placed and would have the order ID, order item ID, the item for which the order is placed, and order account ID. We have two foreign key constraints, the order item FK linking the order item ID to the item ID of the items table, and the order account FK linking the order account ID to the account ID of the accounts table. Finally, we have a temp table with one column. We are then inserting three customers with ID 1, 2 and 3 in the customers table, an account for each of the customers with ID 1 for customer ID 1, ID 2 for customer ID 2 and 3 for customer ID 3. We insert a couple of items with ID 1 and 2 in the items table. Finally, we have the commit. Let's run this script. Everything went successfully. Let us create a package account management which has just one variable gdebit of type varchar2 with an initial value of n. Let's compile this. Let us create a sequence, orders sequence, with the command create sequence orders sequence start with 1 increment by 1. We will use this sequence to generate the order ID while inserting in the orders table. Let's create this. So here is the procedure process order which we are using to place an order. It takes P account ID, the account ID placing the order, P item ID which is the item ID for which the order is being placed, and the item value P item value. We have defined two variables LNewBalance and LBalance again, both of type accounts.accountBalance percentage type. The begin keyword begins the execution section. We can name this transaction using the command set transaction name place order. This would be useful if this was a long-running transaction and we wanted to monitor it. In our case, however, it will finish fast and we would not be able to take a look at the $V transaction table as it is removed from there as soon as the transaction finishes. First, we debit the account for the item value by issuing an update to the accounts table, reducing the balance by the P item value for the past account ID, fetching the new balance by using the returning into clause in the LNewBalance variable. We then print using DBMS output account ID debited for P item value, new balance is LNewBalance. We are then setting the package variable accountManagement.gDebit to a value of Y. We print a message stating that. Then we insert into the orders table the order, generating the order ID using the orders sequence for the item ID and account ID. We then print successful insertion in the orders table. If everything goes well, we commit. In case of an error, we have an exception block. In the exception section, we first select the account balance for account ID 1 at this point of time before calling the rollback. Based on the statement level atomicity, the error in the insert statement should not affect the update and it should still have the reduced value over here. We print using DBMS output.putLine statement in exception section balance for account ID 1 before rollback and print the L balance again. Then we print the error message using DBMS utility.formatErrorStack and formatError backtrace. We issue the rollback and then again print the package variable accountManagement.gDebit at this time. It should still retain the value assigned to it as rollback does not roll back the package level variable assignment. Let's compile this procedure. Let us first select from the accounts table. As we can notice, all the accounts have a balance of $1,000. Let's select from the items table. There are two items, item ID 1 and 2. Let's select from the orders table. It currently has no orders. Now let us run the procedure exec process order passing account ID 1, placing the order for item ID 3, which does not exist, for $200. We are purposely passing a wrong item ID to raise an error during the insertion in the orders table. Let's run this. As expected, the update was successful and account ID 1 was debited for $200, bringing its new balance to $800. The package variable accountManagement.gDebit was assigned a value of Y. While trying to insert, there was an error due to integrity constraint violation, and the execution flows to the exception section where, before rolling back, we print the balance for account ID 1, which is still $800. This demonstrates the statement level atomicity that the error caused in the insert statement did not cause the work done by the update statement to be rolled back. The rollback was issued. The value of the package variable accountManagement.gDebit after the rollback is still Y. So this demonstrates that the package level variable value does not revert back due to rollback statement. Let's check the balance in the accounts table. The rollback was successful as all the accounts still have a balance of $1,000. Let's check in the orders table. There is still no order inserted. What happens if we issue a DDL statement in between our transaction? So here, after the update I have put in, execute immediate drop table temp table command. Execute immediate is a dynamic SQL command. Do not worry too much about its syntax at this point of time. Just know that we are issuing a DDL statement over here. Let's compile our procedure again. Let us execute our procedure, process order again, where we are trying to raise an error by passing an invalid item ID of 3. As before, the update statement was successful, reducing the balance of account ID 1 to $800. The package variable account management.gdebit was assigned a value of Y. Trying to insert into the orders table again raised an exception, and in the exception section, account ID 1 has a balance of $800 before the rollback statement. The rollback statement was issued. The value of the package variable account management.gdebit after the rollback is still Y. Let us select from the accounts table. This time, the balance has been committed to $800, demonstrating that the DDL statement issued an implicit commit. This is something you need to be careful of. Now back to our procedure, process order. Let's comment the execute immediate statement and let's compile again. Let us execute our procedure, process order again, but this time let us change the item ID to 1, which has a value of $600. Let's run the procedure again. The update was successful. Account ID 1 was debited for $600, bringing its new balance down to $200 from the previous $800. Package variable account management.gdebit was assigned a value of Y, and this time, since the item ID was valid, there was a successful insertion in the orders table. Let's query the accounts table. The new balance of $200 was successfully committed. Let's query the orders table. The order was placed successfully for account ID 1, so the commit made the changes permanent. Let us now talk about SavePoint, which is another transaction control statement. The syntax for defining a SavePoint is SavePoint followed by SavePoint name. So a SavePoint is a user-defined marker within a transaction. A SavePoint helps you break a really long transaction into logical chunks. So creating a SavePoint makes sense when you can identify logical groups within a transaction, which would be okay to commit as a logical unit even though the main transaction fails. We will explain this more shortly. You can have multiple save points within a transaction, and you're not just limited to 1 or 2 save points. Save points enable you to do partial rollbacks. So for instance, if there is a failure in a statement after a save point, instead of issuing a rollback which goes all the way to the beginning of the transaction, you can ask it to be rolled back just to the save point. So only changes made after the save point would be rolled back, and the changes made before the save point would still stay. Oracle will release all locks it acquires because of changes it made after the save point. So let us understand save point with an example. Let us say that instead of one order, we have 2 orders to place, and we are trying to place both orders as a part of a single transaction. In each order, we debit the account for the item value and then insert the order in the orders table. Each order by itself is a logical, complete unit of work, and so we can break the transaction into 2 parts and place a save point in between, which we are calling as save point after first order. Now let us say that order 1 goes through fine, but during the placing of order 2, say while inserting in the orders table, there is an error causing an exception to be raised. Inside the exception block, we print the error message and what went wrong. Then we roll back to save point after first order. Typically in the exception section, you might want to log the problem in a log table, and you have to place it after the rollback statement and before the commit to make sure that it is not rolled back too. So the save point allows us to only undo the changes made in the second order while still allowing us to commit the first order. This is just a simple example to demonstrate how save points can be declared and used. You would use them in situations where you have a transaction which can be logically split into groups, and you do not want to start all over again when a statement way down in the transaction fails. You can have multiple save points in a transaction. For instance, here after the first insert, we have defined save point first. Then after update and any other statements after that, we have defined save point second. It is not required to have more than one statement in order to define a save point. If you want, you can define a save point after each statement, though practically you will not do it in most cases. After the insert statement, we define save point third. Now let us say somewhere down, based on some condition, we decide that we want to roll back to save point second. So at this point, whatever work we had done after save point second is rolled back, and the state of the data goes back as at save point second. With this rollback, we have erased save point third. It now no longer exists. Save point first still exists though. Also, any locks placed on rows after save point second are released. What if we just issue the rollback statement? In that case, the transaction will be rolled back to the very first statement, erasing all the save points in between. So here, if I just say rollback, it will go all the way up and undo everything including the first insert. If you define a save point with a name which is the same name for a save point defined earlier, Oracle will overwrite the old save point with the new one. So the old save point is no longer there and the marker is now moved to the new save point. Here is an example of how you might use save points practically. Say we have a table which holds the order queue information, and we have a PL/SQL process which processes the orders one by one in a batch. Let us say we have a cursor cur_get_order_queue which fetches the order info. We write a cursor loop in which we fetch the data in the order var. In the beginning of the loop, we set a save point before order. We then open a block inside which begins with the begin statement. Then we perform the debit via the update to the accounting table and then insert the order in the orders table. If everything goes well, we do a commit. However, if there is an error in any statement and it goes to the exception block, then we roll back to save point before order, thus rolling back that order only. Then we log the error, recording the count ID, item ID, and the reason for the error. We commit afterwards to commit the insert to the log table inside the log error procedure. So every time in the loop, the save point is overwritten, setting it just before the current order being processed. This way we process all orders which go successfully, as well as also record orders which have errors in one loop without having to start over and over again. In this demo, we will see how to set up save points and use rollback statement to explicitly go to it in case of an error. We will also see how declaring a save point overwrites a previous save point with the same name. We will demonstrate how using save points we can ensure that we process all orders in one go, recording the ones that fail and processing the rest. First, let's update all the accounts to a balance of $1,000. Let us delete anything we might have inserted into the orders table and then commit. Let's run these statements. Now here is an anonymous block where we are processing two orders. We have declared L account balance 1 and L account balance 2 to hold the new balances for the two accounts after placing the order. We start with the first order and update accounts, setting the account balance to account balance minus 600, bringing it down to 400 for account ID 1. Using the returning clause, we return back the new balance into L account balance 1. Using DBMS output, we print the new balance. Next, we place the order by inserting in the orders table for order ID 1, item ID 2, and account ID 1. We then establish a save point, save point after first order at this point of time. Next, we start the second order. We again debit account ID 2 for $600 and get a new balance of $400 into L account balance 2. But now, while inserting the second order, we are purposely inserting a wrong item number 10, which does not exist. This would cause a referential integrity constraint to be violated, raising the error to the exception block where we print some messages and then roll back to save point after first order. Then we commit. We expect the rolling back to save point after first order should revert only the update to account ID 2, and then the subsequent commit should commit the changes for the first order. Let's run this block. As expected, we debited account ID 1 for $600, bringing the new balance to $400. We inserted in the orders table for account ID 1. We then established save point after first order. The second order started, and the update to account ID 2 was successful, bringing the balance down to $400. However, while inserting, there was an error inserting for the second order due to referential integrity violation. We then roll back to save point after first order and then commit. Let us now take a look at the accounts table and the orders table. Let's first select from the accounts table for account ID 1 and 2. Account ID 1 was debited, bringing the balance down to $400. Update to account ID 2 was rolled back successfully, restoring the balance to $1,000. Let us now examine the orders table. The order was successfully placed for account ID 1 as expected. For the next demo, let us create an orders queue table where we queue up orders for batch processing. It has a queue ID, queue account ID, the account ID placing the order for queue item ID. First, let us update the account balances for accounts 1, 2, and 3 to $1,000 each. We then insert in the orders queue table 3 orders, one for account ID 1, next for account ID 20, which does not exist and should error out during processing, and lastly for account ID 3. Each one is placing an order for item ID 2, which is worth $600. Next, let's flush out the orders table and commit. Let's run these statements. Let us insert another item, item ID 3 in the items table and commit. Now next is a procedure we use for batch processing called batch processing. We start off by declaring a cursor, cur_get_orders, where we get the queue account ID, queue item ID, and item value, making a join between the orders queue table and the items table on the item ID. Inside the execution section, we open the cursor for loop, getting the results in orders var. We first establish a save point at the beginning of the loop called save point before order. So before each order, this will be set and will override any save point set earlier in the loop. Next, we have a block inside the loop which we have created so that the exception is caught inside the exception section, and then it again goes back to the loop. Inside, we process the order, updating the account, reducing its balance, and then inserting in the orders table. If all goes well, we commit. Then we have an exception section where we roll back to save point before order, erasing the changes made for the last order in the loop. Using dbms output, we output the account ID, item ID, and the error message. You would most probably have a call to a log table to log the error over here. The way we have inserted the orders in the orders queue table, the second transaction would fail, but since we have a save point, we can just roll back the second order and still commit the first order and the third. End batch processing ends the procedure. Let's compile this procedure. The procedure was successfully compiled. Let us now execute this procedure by calling exec batch processing. From the output, we notice that it processed order for account ID 1, order for account ID 20 failed as it does not exist, and order for account ID 3 processed successfully. Let us now check the account balances. The balance for account ID 1 and 3 were indeed reduced to $400. Let us look at the orders table now. The order was successfully placed for account ID 1 and 3. So using save points, we could process all the orders in one go, recording the ones that failed and processing the rest. One of the major benefits and strength of using Oracle database is its efficient and optimized lock management. It allows different sessions to read and write data without interfering with each other, and at the same time ensuring that the locking time is reduced to a minimum. Generally, you would want to leave it to Oracle to handle the locks for you, but in certain situations, you might want to have more control of the locks. Oracle provides you mechanisms to do that. For instance, a couple of ways to do that is by the use of the cursor for update statement and the lock table statement. Let us take a look at them. When you open a cursor and fetch a set of rows based on a query, Oracle does not log them right away. It only logs them once you have changed them. This helps in reducing the locking time to a minimum and increases general availability. But then there is a chance that some other session can obtain the same row and change the data and commit it before your session gets a chance to issue an update and log the row. The cursor will have a snapshot of the data from the point of time it was opened, and it will not be able to see the latest data change committed outside your session. And if your change is based on a certain column having a certain value, and if it was changed by another session, your cursor, which still sees the old data value, will make the update based on that, thus causing incorrect updates. It will make the changes without knowing how the data last looked. Sometimes you might want exclusive lock on rows right from the time you select them in your cursor to ensure that no one else can change it outside your session. These records will be available to others only after your session issues a commit or a rollback. This ensures that as you iterate over the rows in your result set, you can be certain these are the most current values. Cursors for update can help with these kind of situations. We spoke about these in detail in the cursors module of the part 1 course, so I will just briefly touch upon them over here. So say we want to impose a fine of $10 for all accounts having a balance less than $500 at month end. So we have a cursor, cur update accounts, which takes in p balance of type accounts.accountbalance percentage type, which selects account ID, account balance from accounts where account balance is less than p balance for update of account balance. Using the for update of account balance makes it a for update cursor, and Oracle will obtain locks on the rows fetched from the cursor as soon as it is opened. Inside the execution section, we open the cursor in a loop and update the account, setting the balance to be account balance minus 10 using the special keyword using current of cursor to identify the current row in the loop. The commit will end the transaction and release the locks. So since this update is based on the account balance being less than p balance, the for update cursor ensures that at the point of time when we issue the actual update to the accounts table, the balance is still less than 500 and that the rows obtained by the cursor are locked until this session issues a commit. Oracle, as I mentioned before, tries to minimize locking to provide high availability and concurrency, at the same time ensuring data integrity and asset transactions. So in most situations, I would leave it to Oracle to manage locks. There are shared locks and exclusive locks. For example, many users can have row share locks on a table, but only one user can have an exclusive lock on the table. Once a table is an exclusive lock, it prevents other users from inserting, updating, or deleting in the table. When a transaction tries to insert, update, or delete a row, it obtains a row exclusive lock on those rows, and if another session wants to act upon the same rows, then it has to wait until the first one finishes. Locks never prevent querying of the data, and a query will not obtain table lock. I will not go in much detail over these. In most situations, you would not need to use these in PL/SQL programming. Lock table accounts in row share mode no wait would enable you to acquire a row share lock on the table and telling Oracle not to wait and come back right away if it cannot obtain the lock. Row share lock allows concurrent access to the table but would prevent any other session from getting an exclusive lock on the entire table. With lock table accounts in the row exclusive mode, the transaction would acquire a row exclusive mode lock on the table. When you commit or roll back, these locks are released. Understanding how transactions work and can be managed is very important while writing PL/SQL code. Oracle Database has a very powerful transaction management framework. Oracle provides locks and read consistent snapshots automatically in an optimized fashion in order to provide high availability and concurrency along with asset guarantee for the transactions. It provides us with mechanisms like commit, which makes the changes permanent, rollback to undo the changes, and save point, which allows us to put markers in between transaction boundaries to which we can go programmatically. Lock table statements are available if you want to have more control, but generally I would leave it to Oracle to manage locks automatically. Hi, welcome to Pluralsight. My name is Pankaj Jain and welcome to this module on autonomous transactions. Autonomous transactions is a very neat feature introduced with Oracle version 8i, which allows us to initiate independent transactions from within a parent transaction. That has enormous use for logging, usage monitoring, and a lot of other tasks. It allows us to do tasks which otherwise would take a lot of complex coding and require a complex setup of database pipes and jobs. It has a very simple syntax but packs a lot of punch in providing us with powerful functionality with amazing ease. Let us learn more about this important feature. What is an autonomous transaction? As I mentioned earlier, an autonomous transaction allows us to initiate an independent transaction from within another outer transaction. It is not affected by commits, rollbacks, or save points initiated in the outer transaction and does not share any context information of the outer transaction. It is a pragma directive. A pragma directive is a compiler directive which is processed at compile time and not at runtime. The pragma passes the relevant information to the compiler. Why should you use or need to know about autonomous transactions? Autonomous transactions allow you to easily accomplish certain tasks which otherwise would require a lot of complex setup and coding. Some of the common uses of an autonomous transaction are logging. Sometimes you want that the log information be saved even if the main transaction is rolled back. You can try and do it by calling the logging procedure after the rollback and issuing a commit right after that, but it makes the coding more complex and sometimes it may get a little tricky and may not be possible. Autonomous transactions take away all that complexity and provide an easy, straightforward way to accomplish that. Another place they can be used are in usage counters for, say, software programs, where you want to restrict the program usage only to a certain number of times, or in general track the program usage. You can use them to track the retry counters, say when a user is trying to log in. In general, it helps in creating modular reusable code. It helps you encapsulate business logic and call it in an independent fashion. It is extremely simple to define an autonomous transaction. Its syntax is pragma autonomous transaction followed by a semicolon. It can be defined in the declaration section. It can appear anywhere within the declaration section, but as a good programming practice, I like to declare it as the first thing in my declaration section. Where can the autonomous transaction be defined? They can be defined in a top-level anonymous block. For instance, here is an anonymous block where we are inserting some information in the log table. It has the pragma autonomous transaction as the first thing in the declaration section. This is followed by L account ID of type accounts.accountID %type, followed by L message, which is a varchar2 given a value of test. In the execution section, we insert in the log table the log ID using a sequence log sequence.nextVal. NextVal is a keyword which fetches the next value from a sequence. We insert the L account ID, L message, and the system timestamp. Finally, we commit and end the transaction. Autonomous transaction pragma, however, cannot be defined in a nested block. So here, if we try and define it in a nested block, Oracle will raise errors. Pragma autonomous transaction can be defined in standalone procedures, as shown in this example, where we have defined it after the is keyword and before the execution section begins. It can be defined in standalone functions too. Here is a function, log message function, which returns a number. The pragma autonomous transaction is defined after the return clause and before the execution section begins. The autonomous transaction pragma can also be defined in packaged procedures and functions. It cannot be defined in the specification section. It has to be defined in the package body section. So for instance, we have defined the pragma for the procedure log message after the is keyword. We have also defined it for the function log message function after the return clause and before the begin keyword. It is not necessary that all the procedures or functions have this pragma. You can have it only with the ones you want. We haven't talked about triggers yet, but triggers are program units you tie to a table, view, schema, or the database. They fire automatically when an event happens, like say a trigger defined to fire whenever an insert happens in a table. Database triggers cannot issue commits or rollbacks, but if you define them as autonomous transactions, then they can. This is a feature which might be useful for auditing, where you want to have the audit information committed even when the insert is rolled back. We haven't talked about SQL object types. Oracle Database supports object-oriented programming. You can create objects and define methods and attributes on them. You use PL/SQL to code the methods. These methods can also be defined as autonomous. Let us understand what happens when an autonomous transaction is initiated from a main transaction. Here is our procedure process order again, which we are using to place orders for a passed P account ID for a given P item ID of value P item value. We first debit the account and reduce its balance. Next, we want to log our action using a procedure log message, which is defined as an autonomous transaction. The log message procedure is a simple procedure which takes in P account ID and the log message and inserts it in the log table. It is defined as autonomous transaction using the pragma. Now let us understand how the transaction flows. The update statement will start the auto transaction. Next, log message is called, which will transfer the execution to the log message procedure. When the log message procedure starts, it will suspend the auto transaction. The insert into log table statement will start the autonomous transaction. When we commit later, this will end the autonomous transaction. When the log message procedure completes, the auto transaction resumes. The execution flow goes to the next statement after the log message procedure. Finally, the commit in the process order procedure ends the auto transaction. Every autonomous transaction which issues a DML should be ended by a commit or a rollback. Of course, if it is not doing any DML like insert, update, and delete, then commits and rollbacks are not needed. But there is not much point in creating an autonomous transaction anyways if we are not doing any DML inside them. If you do not put a commit or rollback inside, Oracle will still allow you to compile them, but when executing them, it will raise an error aura-06519, active autonomous transaction detected and rolled back. If an exception is raised inside an autonomous program unit which goes unhandled, then Oracle will automatically roll back the transaction. So say, inside our log message procedure, we are also doing some housekeeping every time it is run. We delete all messages older than 7 days first, and then say later in the insert statement there is an error. Since there is no exception block to handle the error, it will be raised to the calling client unhandled, and Oracle will automatically roll back the delete made by the first statement. The exception will flow to the exception block of the outer program if it exists, as it does with normal exception propagation when one program calls another. What are the valid transaction management commands we can use inside the autonomous transaction? Well, you can use all the familiar commands like commit, rollback, savepoint, and the setTransaction command. And you're not limited to having just one commit inside it. You can have multiple commits if you need. So here, if we wanted it for some reason, we can issue a commit after the delete from the log table first, and then again issue a commit after the insert statement. You can in the same way have multiple rollbacks or save points inside your autonomous transaction. The only thing to take care of is that there is no change which is either not committed or rolled back when you come out of the autonomous transaction. Let us understand the need for autonomous transaction with an example. Let us take a look at our procedure, process order, which takes in P account ID, placing order for P item ID of value P item value. Inside, we first debit the account by issuing an update and reducing the account balance of P account ID by P item value. Then we log a message passing in two parameters, P account ID and the message debited. Later, we insert the order in the orders table. Then we log a message again for P account ID with a message order placed. If everything goes well, we issue a commit. If, however, there is an error, then inside the exception block in the when others handler, we log a message for P account ID, putting in the error message returned by the SQL ERRM function. Now here is our log message procedure, which takes in two parameters, P account ID and P message. It simply inserts in the log table. As the log message procedure stands now, if there is an error, say while doing the insert in the orders table, the execution will flow to the exception block, and the rollback over there will roll back not only the update to the accounts table, but it will also roll back the log message inserts in the log table. But what if our requirement is to log the messages even if the transaction is rolled back? Autonomous transactions can come to our rescue in this situation. Let us make a slight change to the log message procedure. Let us just add the pragma autonomous transaction statement at the beginning of the declaration section. Let us add a commit at the end. This simple command packs in a lot of punch and would enable us to run the log message procedure in a transaction of its own, unaffected by the rollbacks, commits, or save points in the outer transaction. So now the rollback can revert changes to the accounts table, but inserts in the log table will persist. An autonomous transaction does not share the transaction context with the outer transaction. So it does not share the commits, rollbacks, save points, locks, object changes, and resources of the outer transaction. To illustrate the point, let us look at our procedure process order again. Let us say after the update to the accounts table, we issue a save point by the name of first. Then we call the log message procedure, inside which we again establish a save point with the same name first in the beginning. This save point is different from the save point in the outer transaction, and it would not overwrite it. After the log message procedure finishes and the execution comes back to the process order procedure again, executing rollback to first will take us to save point first in the process order procedure. it will not roll back the insert we did in the log table, as that got committed independently in the autonomous transaction. Once the autonomous transaction is completed, the changes committed by it are visible to the main transaction as well as the other sessions. So in this procedure, we are inserting in the log table using the log message procedure by passing an account ID 1 and a message account 1 debited. Inside the log message procedure, which is an autonomous transaction, we insert in the log table. When the execution resumes to the main transaction, if we have to query the count from the log table where log account ID is 1, we will get a value of 1 in our main transaction. Say we have another session outside, and if it queries the count from the log table for log account ID of 1, it will also get a value of 1. This is the default behavior. However, if you do not want this to happen, you can set the isolation level to serializable for the main transaction using the command set transaction isolation level serializable. Then the main transaction cannot see the changes made in the autonomous transaction when it resumes. Transaction mode serializable would allow only serial execution of transactions versus concurrent execution. You should not be using serial mode generally, as it severely compromises performance, but I just wanted to mention the behavior in case this isolation level is set. In this demo, you will see how to create an autonomous procedure and also demonstrate a common usage scenario for it, which is application logging. First, let's create a logging table called log table, which has a log ID, a log account ID, a log message column, and a log insert time. We create a sequence log sequence to insert in the log ID. We create it as create sequence log sequence start with 1 increment by 1. Let's run these statements. Next, we create a procedure to log messages, log message, which takes in p account ID of accounts.accountID% type and p message of type varchar2. We insert in the log table the log ID using the log sequence.nextVal, log account ID as p account ID, and log message as p message. As it is defined now, it is not an autonomous transaction. Let's compile this procedure. Let us now create the procedure process order, which takes in the account ID p account ID, placing the order for p item ID of value p item value. We first debit the account by updating the accounts, setting the account balance to be account balance minus p item value for account ID equal to p account ID. We log the message p account ID debited. Then we place the order by inserting in the orders table. We log the message p account ID order placed and then commit. If there is an error, say during the insertion in the orders table, the execution will flow to the exception block where we log the message again with p account ID and SQL ERRM and then roll back, finally raising the error to the calling client. Let's compile this procedure. Let us first select from the log table. There is nothing in there right now. Let us now execute the process order procedure passing an account ID 1 and invalid item ID 3 with an item value of $200. Let's execute this procedure. Since the item ID is invalid and we have a referential integrity constraint on the orders table linking it to the item ID of the items table, the insertion fails, making it go to the exception section where everything is rolled back. At this point of time, if we query the log table, there is nothing in the table as the rollback statement rolled it back. However, we wanted the log information to stay even though the main transaction was rolled back. This can be easily accomplished using the autonomous transaction. Let us go back to our log message procedure and add the pragma autonomous transaction at the top. We have to end it with a commit. Let's compile it again. Let us run the procedure again with the same parameters. It again failed due to referential integrity violation during the insert to the orders table. Everything was rolled back. Let's query the log table again. This time, the information in the log table was saved. This shows the simplicity and power of the autonomous transaction pragma. In this demo, we will see how autonomous transactions maintain their own transaction context independent of the parent transaction. First, let's delete everything from the orders table and the log table, update the accounts, setting the account balance to $1,000, committing the information, and then let's select from the accounts table. There are two accounts with account ID 1 and 2. Here is the log message procedure again, which is an autonomous procedure. Let's first establish a save point called save point first over here. Then we insert in the log table. Let's compile this. Next, we have an anonymous block. Inside the execution section, we first establish a save point called first. Notice that this is the same name we had established of the save point in the log message procedure. Then we insert in the accounts table account ID 10. Next, we call the log message autonomous procedure passing account ID 10 and a message created. After this, we execute a command roll back to first. Since the autonomous transaction does not share the transaction context with the main transaction, the save point inside it is totally different from the save point first in the anonymous block. So the command roll back to first would take it back to the save point before the insert in the accounts table and would not roll back the autonomous transaction which is independent. Let's run it to confirm. Querying again from the accounts table, we see that there are still the two account IDs 1 and 2, and insertion for account ID 10 was rolled back. Selecting from the log table, we notice that the insertion in it was successful and committed. It was not affected by the rollback to save point in the anonymous block. So this demonstrates that autonomous transactions do not share the transaction context like locks, resources, save points, etc. with the main transaction. An autonomous transaction is an atomic unit of work. It allows you to encapsulate a piece of business logic which can be then run atomically. For instance, if you wanted to have the placing of a single order considered as an atomic unit of work, you can call the process order procedure as a pragma autonomous transaction. Now each order is encapsulated as an atomic unit of work. So now what you can do is that if you have an orders queue, then you can get the orders one by one in a loop using a cursor cur get orders queue, and then in the loop call the procedure process order. You do not have to worry about committing orders which pass and rolling back the ones which fail, as running the process order procedure as an autonomous transaction takes care of that for us. We can call one autonomous transaction from within another autonomous transaction. Each one will work independently of the other, and they would not share the transaction context of each other. We can have our process order procedure, which is defined with pragma autonomous transaction, called the log message procedure, which is also autonomous. Each one will be committed or rolled back independently. In this demo, we will demonstrate another common usage for autonomous transactions where they help in encapsulating business logic and forming an atomic unit of work. We will also see how autonomous transactions can be nested and their behavior. We will be using the orders queue table we had created in the transactions module and show how autonomous transactions can help simplify the logic and make it accurate. Let's first select from the orders queue table. We see that there are three orders. There is an order from account ID 1 for item ID 1, account ID 10 for item ID 2, and account ID 2 for item ID 1. Account ID 10 does not exist. Let us now delete everything from the orders table and the log table and commit. Here is our process order procedure. We have made it autonomous by including the pragma autonomous transaction at the top. So processing a single order becomes an independent atomic unit of work. It again takes in the account ID, item ID, and item value parameters, debits the account, and then inserts in the order table and then commits. Using the autonomous log message procedure, it logs the account ID and order successful message. In case of an error, it goes to the exception block where everything is rolled back, and using the autonomous log message procedure, we log account ID and the message failed concatenated with the SQL ERRM function. This would demonstrate nesting of autonomous transactions. The process order procedure is an autonomous procedure, and it calls the log message procedure, which is also autonomous. Let's compile this procedure. Now here is an anonymous block where we have declared a cursor cur get order queue, which selects the queue account ID, queue item ID, and item value from the orders queue table, joining it with the items table on the item ID. Inside the execution section, we open a cursor for loop and get the information in the cur info var. Inside the loop, we call the autonomous procedure process order, passing the queue account ID, queue item ID, and item value. Running it this way, we do not have to worry putting save points to roll back unsuccessful orders. We expect the first and third orders to process and the second one to fail. Let's run this anonymous block. Now let us look in the orders table. As expected, we see that orders for account ID 1 and 2 were inserted successfully, but not for account ID 10. Let us now select from the log table. We see that it logs the successful completion message for account ID 1 and 2 and also logs the failure for account ID 10 with the error message regarding integrity constraint violation. So this demonstrates how an autonomous subprogram can be called from within another autonomous subprogram and how autonomous transaction pragma helps us create independent atomic unit of work. In this module, we talked about what autonomous transactions are. They are transactions which can be launched independently from within a main transaction. They can be defined in outer level anonymous blocks, standalone procedures and functions, package procedures and functions, database triggers, and object methods. It has an amazingly simple syntax and allows us to achieve functionality which otherwise would require very complex coding and setup. It has use in logging and auditing applications, tracking program usage, retry counters, and in general encapsulating business logic to create independent atomic unit of work. We talked about some considerations like having a commit or rollback to end an autonomous transaction, and that any unhandled exceptions will cause the changes to be rolled back. Autonomous transactions do not share transaction context like commits, rollbacks, and save points with the main transaction. Hi, welcome to Pluralsight. My name is Pankaj Jain and welcome to this module on native dynamic SQL. Dynamic SQL, as the name indicates, allows you to write SQL which is dynamic. The SQL statement is determined at runtime based on, say, user input parameters or some processing logic. It helps us write extremely flexible and reusable code. In this module, we will take a look at native dynamic SQL, one of the ways of executing dynamic SQL. We will talk about advantages and some common usage scenarios for dynamic SQL. We will see how to perform selects, inserts, updates and deletes, as well as execute DDL statements and anonymous blocks inside PL SQL using dynamic SQL. We will also talk about SQL injection risks associated with using dynamic SQL and some best practices related to that. In the next module, we will take a look at dbms_SQL package, another way of executing dynamic SQL, which has some unique advantages compared to native dynamic SQL. Knowing to write dynamic SQL is very important to be fully proficient with PL SQL and to take care of various usage scenarios and business needs. So let's take a closer look at this important topic. So what is dynamic SQL? As we said earlier, for dynamic SQL, the SQL statement is not known until runtime. Let us understand this by comparing a code snippet which has static SQL versus a code snippet which has dynamic SQL. So here is a simple function getCount which takes in a parameter paccountID of type accounts.accountID %type and returns a number. It has lcount, a number variable. Inside the execution section is the SQL statement select count star into lcount from orders where order account ID is equal to p account ID. Now this is static SQL which we have been using so far. The select clause, the table in the from clause and the where conditions are all known to the compiler when it goes to compile the function. Compare this with this function rewritten for dynamic SQL. It takes in a parameter pwhere of type varchar2, which is the user-defined where condition not known until runtime. Again, it has lcount variable of type number. But here, lSelect variable is defining the select clause of select count star. lFrom is defining the from clause of from orders, and then we have a variable lQuery of type varchar2 200. Inside the execution section, we are building the query string lQuery, concatenating the variables lSelect, lFrom, and the where condition using the parameter pwhere. Using execute immediate, which is the native dynamic SQL syntax, we run this query and get the result in lcount. Do not worry too much about the native dynamic SQL syntax, as we will talk in more detail about it soon. So as you can see here, the SQL is assembled at runtime using variables. So until the time this block is run, the compiler has no idea as to what SQL is going to be run. Since the select clause, where clause, etc. are all variables, you can change their values anytime in the code based on certain conditions, giving you the flexibility to run different queries for different conditions. This is dynamic SQL. So having taken a brief look at dynamic SQL, let us compare it with static SQL. Some of the obvious differences are that for static SQL, the compiler knows the SQL at compile time versus for dynamic SQL, where the compiler does not know of the SQL until runtime. Since the compiler knows the SQL at compile time, it can verify the object references and do the syntax checks during compilation, which it cannot do for dynamic SQL. So the chances of runtime errors are more in case of dynamic SQL if invalid objects or syntax is specified using variables. Similarly, for static SQL, the compiler can verify the object privileges during compilation, which it cannot verify in the case of dynamic SQL. With static SQL, the PL SQL compiler does early binding during compile time. Early binding is the process by which it allocates space for the identifiers, checks for permissions, valid object references, etc. Since Oracle Database allows the ability to compile and store the program units in the database, even though early binding requires longer compile time, this is an efficient model for faster runtime execution. With dynamic SQL, it does late binding, where the compiler parses the SQL statement at runtime. Since we have to specify everything at compile time, it makes static SQL less flexible. And this is where the major advantage of using dynamic SQL comes in. It is extremely flexible and creates highly reusable code. Since the checks and verifications are done at compile time, static SQL is faster than using dynamic SQL, where these validations are done at runtime. So in general, if you do not need a degree of flexibility and dynamism in your code, which dynamic SQL provides, you should stick with using static SQL. If you see yourself doing a lot of code duplication, say in the previous example of the getCount function, if you were creating several versions of the same function based on different where conditions, or using a lot of hard-coded ifs to use different versions of queries, then it might make sense to use dynamic SQL. Let us look at some of the common usage scenarios where dynamic SQL might be useful. It is useful where your queries are dynamically changing. Say you have a web application where you allow the users to specify the query criteria for the information they want to see against a table. Then it might make sense to create a dynamic function which takes in a select clause and a where clause as parameters, allowing us to reuse it for any variant of user-specified query criteria. Dynamic sorts is another place where on the web page we might want to allow the users to specify the sort criteria for the information requested. Then we can from the get-go get it in the right order from the database function. Dynamic SQL would enable us to do this easily. You might have modular functions or procedures you want to execute for certain conditions. You can do hard-coded ifs and else ifs to call them, but then if you have to change them very often, it would be a lot of work. Instead, you can store the condition criteria to the subprogram name mapping in a table, which you can read to get the subprogram name for a given condition and execute it dynamically. Sometimes you might use naming conventions to build a function or procedure name based on conditions or input data and then execute them. For example, if you want to process order in a specific way for each customer and you have created versions of procedures, say called process order customer A, process order customer B, etc., then based on the past customer name, you append it to the process order string to build the procedure name and then invoke it dynamically. Oracle also allows you to specify hints while running queries, which can alter the way the query is run by the optimizer in order to make it more efficient based on the information you know. Using dynamic SQL, you can pass the hint as an input parameter, construct the SQL statement using that hint, and execute it. DDL statements like create or drop commands can be run in PL SQL only using dynamic SQL. Traditional static PL SQL only allows DML statements and transaction control statements, as these do not alter objects or privileges, thus enabling early binding. DDL statements can potentially alter these, thus these are not allowed except by using dynamic SQL, where the binding does not have to be done until runtime. Dynamic SQL is useful for tools who rely heavily on looking up information from Oracle Data Dictionary to build up SQL statements or execute procedures, etc. dynamically. Dynamic SQL is also useful in scenarios like where the table name or the schema object names in the database are frequently changing and you want to use a pattern based on certain conditions or user input to construct them dynamically and invoke them. These are just some of the common usage scenarios I can think of, but there are many more which you might discover while working on business problems where dynamic SQL can impart you a lot of ease and flexibility. There are two main ways to invoke dynamic SQL. The native dynamic SQL, a small snippet of which we saw earlier, and then the other method is by using the dbms_SQL package. Native dynamic SQL was introduced later starting with Oracle version 8i. Each one of these ways has its own advantages and drawbacks. We will talk more about the dbms_SQL package in the next module. Why should you use native dynamic SQL? One major advantage of native dynamic SQL is that it is very easy and simple to use. It allows us to place the dynamic SQL statements directly in the PL SQL code and its syntax is relatively simple to understand. It provides better performance than using the dbms_SQL package. In addition to providing a rich set of built-in data types, Oracle Database also allows users to define their own data types if they need to. Native Dynamic SQL supports all the user-defined data types and collections, which dbms_SQL package did not support until version 11G. Native Dynamic SQL supports fetching into records. Records allow us to logically group related items. We will talk about the advantages of using dbms_SQL package in the next module when we talk in detail about it. Let us look at the syntax of the execute immediate statement, which is used for native dynamic SQL execution. It starts with the execute immediate keyword, followed by the dynamic SQL string. This is the string you build based on parameters, variables, etc. Next is the optional into clause. This is used for single row select statements to fetch the returned value into select variables or a PL SQL record. Following this is the using clause, by which you provide bind arguments for any bind variables you might have placed in the dynamic SQL string. Bind variables are placeholders inside your SQL string for which you provide value by bind arguments with the using clause. They are optional to use. If you have no bind variables, you do not have to use these. They have a default mode of in, but can also be passed in the out mode to receive values or in out mode to pass and receive values. Then there is the returning or return into clause, which is used to capture the values returned by the DML statements having the returning clause into bind variables. These are again optional to specify. We will take a look at the various components of the syntax as we walk through various examples. For multi-row selects, along with using the bulk collect feature with the execute immediate statement, you can also use ref cursors. We talked about them in the part 1 course, but here we will take a look to see how we can pass bind variables, etc. while calling them. Let's first take a look as to how to execute DDL statements using native dynamic SQL. Let's start with creating objects like tables. We are defining a procedure create table which takes in the table name and the table columns as input parameters. So using this procedure, we can dynamically create tables. Inside the execution section, we create the table by simply issuing execute immediate followed by the create table string. The create table string is constructed by concatenating create table with ptable name, which is concatenated with the ptable columns. Notice how simple the syntax is. This one-line command is all that is needed to create the table. So an example of using this procedure is by issuing exec create table, passing in the table name of orders QCA and the columns as a string QID number, Q account ID number, and Q item ID a number within parentheses. At runtime, all these pieces are concatenated together to create a valid table create statement and executed with the execute immediate command. Before we go further, let's talk about how privileges are resolved in native dynamic SQL. Only direct grants work inside stored procedures, and privileges granted via roles are disabled during compilation. So for instance, say user demo created the create table procedure. With the execute immediate statement inside the procedure, a create table command is issued. Let us say that the user demo has not been granted direct create table privilege. We create a role called create table role and assign the create table privilege to this role. We assign this role to the demo user. When user demo tries and executes the procedure using the code snippet, it will get an error for insufficient privileges since the user demo does not have the create table privilege assigned to it directly. So to make it work, there are two options. Prior to Oracle 12c, you would have to grant create table privilege to the user demo directly. Then the execution would be successful. Starting with Oracle version 12c, you can assign roles to procedures. So we can assign the create table role to the create table procedure. This is called code-based access control, and with that, the privileges checked for dynamic SQL will be the privileges granted directly to the owner of the subprogram as well as the privileges granted via the role to the subprogram unit. This would help limit the number of direct grants you need to give to the subprogram owner. So if we wanted the users in our system to be able to create tables only using the create table procedure and not directly, we would not grant the create table privilege to them. They just need to have the execute privileges on the create table procedure. Since the procedure has the create table privilege assigned to it via the role, it can do the necessary job of creating the table. Let us now see an example of how we can create a dynamic procedure which can be used to drop tables. This procedure called drop table takes in the table name parameter, which is the table name to be dropped. Inside the execution section, it issues the native dynamic command execute immediate drop table concatenated with the p table name to drop the table. An example to use it would be exec drop table passing in the table name orders QCA. Let us see dynamic SQL for DDL statements in action. Here is the procedure create table, which takes in the name of the table to be created, p table name, and the columns p table columns. We have a varchar2 variable L SQL to hold the SQL. Inside the execution section, we construct the SQL as create table concatenated with p table name concatenated with p columns. Using dbms output, we print the SQL statement, and then we issue the statement execute immediate L SQL to execute the DDL statement. Let's compile this procedure. Now, let us execute the procedure as exec create table passing in the table name order QCA and its columns in the right format for a create table statement within brackets separated by commas with the data type specification. Let's run this. We get an error for insufficient privileges. This is because for dynamic SQL, the privileges have to be directly granted to the demo user. Here is another session where we are logged in as a DBA user. Let's run the statement grant create table to demo. Now let's try and execute the create table procedure again. This time it is successful. In the output window, we see the L SQL variable, which is a valid create table statement without the quotes. Let us describe the table by issuing the command describe orders QCA. It comes back with information, and so the table indeed got created. Let us now create a procedure to drop a table the name of which is passed in as a parameter. Inside, we simply issue execute immediate drop table concatenated with the p table name. Let's compile this. Now let us drop the table we created earlier by issuing exec drop table orders QCA. Now when we try and describe the table, we get an error that it does not exist. Here is an example of doing a single row select using the native dynamic SQL. As I mentioned before, the using clause is optional if there is no bind variable. So here in this code snippet, we are creating a generic function which gets the count of a table passed in as a parameter. It returns the count as a number. We declare lCount to hold the count and lQuery to hold the query. Inside the execution section, we define lQuery as select count star from and concatenated with the p table name passed in as the parameter. Then we execute the SQL string using native dynamic SQL as execute immediate lQuery into lCount. Into lCount fetches the selected count in the lCount variable. Pretty simple, right? Now we can execute this function by passing the orders table parameter in this code snippet, which will return the count of items in the orders table. We can then call the same function passing in the items table as a parameter to get the count of the items table. Let us look at an example of using both the into clause and the using clause with select statements. Here is a function getOrderCount, which gets the count of orders from the orders table for the dynamic condition passed in of p column parameter having a value of p value. Inside, we again declare lCount to hold the count and lQuery to hold the query. Inside the execution section, we form the query by concatenating select count star from orders where p column concatenated is equal to colon call value. Putting a colon in front of an identifier makes it a bind variable, and it is inside the quoted string. Then we issue the dynamic SQL as execute immediate L query into L count using p value. So into L count fetches the selected count in the L count variable, and using p value clause we supply the value for the bind variable colon call value. The bind variable can have any name, and we can have more than one. In that case, we can pass their values separated by commas in the using clause. Now in the next code snippet, we invoke the getOrderCount function, passing in the column OrderAccount ID having a value of 1. So this will translate into a query of select count star from orders where OrderAccount ID is equal to 1. In the next code snippet, we pass the column OrderItem ID having a value of 2, which will translate to a query of select count star from orders where OrderItem ID is equal to 2. So this allows us to create a very flexible function which takes in a user-specified criteria to return the results. We can further expand the parameters to take in more column value pairs, and this can be useful, say, for generating reports with user-specified filters and can be the backend behind a self-service reporting web page. We looked at the example of passing the table name earlier for dynamic counts. I just wanted to mention that when we build SQL strings, we have to concatenate the schema object names and column names versus passing them as bind variables. For instance, here instead of concatenating the table name, if we had to pass it as a bind variable with the using clause, Oracle will raise an error of aura 00903 of invalid table name. Similarly, instead of concatenating the column name either in the condition or in the select clause to the SQL string, if we try to pass it in as a bind variable, Oracle will raise errors. Bind variables should be typically used for supplying values to be compared for column conditions, or for inserting or updating column values in DML statements, for returning into clause, or as parameters in subprograms. So here is one typical use of bind variables in a select statement. The passed column name p column in the where clause is concatenated, but the value is passed as a bind variable colon call value. Later we supply the bind argument with the using p value clause. Let us also see how we can improve the performance of our dynamic SQL statement. If you look in the second code snippet, here we are concatenating both the p column and the p value. This is also valid. We do not have to use the using clause in the execute immediate statement here. So both the ways, as in the first code snippet and the second code snippet, are valid. But using it with bind variable in the first code snippet is more efficient. In static SQL, when you write insert, update, and delete statements, Oracle automatically treats the values as bind variables to improve SQL performance. However, in case of dynamic SQL, you have to do it manually. If you do it using bind variables as in the first code snippet, Oracle can reuse the same cursor for different values of p value. However, if you do it the second way without using binds, Oracle will have to open a new cursor for each different value of p value, which is not very efficient. As far as multi-row selects are concerned, you can do it in two ways. We can use the execute immediate statement with the bulk collect feature and fetch them in collection types. Since we haven't covered bulk collect features and collections yet, we will not cover that option right now, but will cover it in a later course. The other way to do multi-row selects is by using ref cursors. Let us take a look at this option. In this example, we will see how we can use ref cursors to create a dynamic procedure called apply fees, which is used to apply a monthly account fee to the accounts. It takes two parameters, p column and p value, through which we can specify the where condition to filter out the accounts where we want to apply the fees. If you pass a null to these, it will apply the fees to all the accounts. We first start by defining a ref cursor by declaring type curref is ref cursor. Next, we declare a variable of this type called curAccount. LQuery is varchar to 400 to hold the query string, and LAccount ID is of type accounts.accountId %type. We begin the execution section by building the query string as select account ID from accounts. Next, we check if p columns was passed in. If it is not null, we further build the query string concatenating where p column equal to colon p value. We have passed in p value as a bind variable, which is an efficient way to do it. Then we open the ref cursor as open cur account for L query using p value. P value provides the value for the bind variable. However, if p column was not specified, then our L query is just select account ID from accounts and we open cur account for L query. Now from this point on, we can do our normal cursor processing, running it in a loop, fetching the account ID into L account ID. We exit when cur account percentage not found. So we can use all the regular cursor attributes over here. Then we update the accounts, debiting the account balance by $10, where account ID is L account ID, and then commit. So this way, using ref cursors, we can process multi-row selects for dynamic select statements. Alright, let us now take a look at an example of fetching into records with dynamic SQL. We covered records in the Oracle PL SQL Fundamentals Part 1 course, but just to recap, records allow us to group related variables together. Using the percentage row type syntax, we can create records which contain an element for each table column, or we can create our own record with user-specified elements. We will see how to create each one and use them with dynamic SQL statement, both for single row select and multi-row selects. So here we are creating a procedure, initiate order, which takes in a user-specified optional where clause. We first define type cur ref as ref cursor, and then we define cur order as type cur ref. Next we define order record as a user-defined record containing two elements, account ID of ordersQ.QAccountID percentage type and item ID of ordersQ.QItemID percentage type. We then declare L order record of type order record. L item record is a record of items percentage row type. L query will hold the query. So inside the execution section, we start L query as select Q account ID, Q item ID from orders Q, and then concatenate it with the p where clause. Using the ref cursor syntax, we open cur order for L query and in a loop fetch cur order into L order record. So both the Q account ID and Q item ID will be assigned to the corresponding columns of L order record. Next we define the exit condition for the loop, which is exit when cur order percentage not found. Now we do a single row select into a record by issuing execute immediate select star from items where item ID is equal to colon item ID into L item record using L order record.item ID, which is the item ID fetched in the order record earlier. And then we call the process order procedure, passing it the various values from the two records like L order record.account ID, L order record.item ID, and L item record.item value, and then end the loop. In this demo, we will see how to do single row and multi-row selects using dynamic SQL, as well as see how to fetch into records. So here is a procedure initiate order, which is used to initiate orders from the orders queue table, and it takes in an optional p where clause to limit the orders it picks up from the queue table for processing. We start off by declaring a ref cursor as type cur ref is ref cursor. We declare cur order as of type cur ref. Next we declare a record, order record having two columns, account ID of type ordersQ.QAccountID percentage type and item ID as ordersQ.itemID percentage type. L order record is of type order record. L item record is another record of items percentage row type. L query will hold the query. Inside the execution section, we start off by building the query as select Q account ID, Q item ID from orders Q and concatenate it with the optional p where clause. Then we print the L query using DBMS output statement. Next, we open the ref cursor cur order for L query. In the loop, we fetch it in the L order record. So Q account ID and Q item ID will go in the corresponding columns in the L order record. We exit when cur order percentage not found. Now we do a single row select using execute immediate select star from items where item ID is equal to colon item ID into item record using LOrderRecord.itemID as the bind argument. Then we call the process order procedure, passing in the appropriate values LOrderRecord.accountID, LOrderRecord.itemID, and LItemRecord.itemValue. We had created this procedure in the transactions module. This procedure debits the account ID for the item value and then inserts the order in the orders table. We end the loop. Let's compile the procedure. Let's first select from the orders queue table. There are two orders, one for account ID 1 and the other for account ID 2. Next, let's delete everything from the orders table, update the accounts with an account balance of 1000 and commit. Now let's execute the procedure initiate order, passing in the filter where condition of where queue account ID is equal to 1. We see the query as it is executed in the output window as select queue account ID, queue item ID from orders queue where queue account ID is equal to 1. Let's select from the orders table now. The order for account ID is indeed over there. Let's now again delete from the orders table and commit. Let's now run it again without a where condition, passing in a null. This time it will have no where condition and it will pick up everything from the orders queue table. Let's select from the orders table again. And this time we see orders placed for both account ID 1 and 2. Let us see how we can use native dynamic SQL to execute DML statements. Let us start with the insert statement. Let us say we create a generic procedure insert record to insert a row in a 2-column table. It takes in the table name, p table name, the first column name, p column 1 name, and its value, p col 1 value, the second column name, p col 2 name, and its value, p col 2 value. Then we use the execute immediate statement insert into concatenate the p table name, open the brackets, concatenate p column 1 name, comma, p column 2 name, close the brackets, the values clause followed by colon, col 1 value, colon, col 2 value, brackets close, and then the using clause to supply the bind arguments for the two bind variables as p col 1 value, p col 2 value. We then commit. As we had mentioned earlier, we are concatenating the column names, however, using bind variables to supply the column values. When you are passing bind variables in execute immediate statements, you have to pass values or bind arguments equal to the number of bind variables, even though there might be a repetition. For every bind variable, there has to be a corresponding bind argument either in the using clause or returning into clause and define variables in the into clause. This is true for all kinds of statements except when we are executing anonymous blocks. We will talk about them later. So for instance, here in the insert statement, even though we are inserting the same bind variable colon col 1 value for both p col 1 name and p col 2 name, we have to pass the value twice in the using clause. Since there are two bind variables, we pass the value twice. Native dynamic SQL supports all the SQL data types like character, date, number types, etc. It did not support the PL SQL only data types like Boolean, etc. until Oracle 12c, where it now supports Boolean, associative arrays with PLS integer indexes, and composite types like records and collections declared in the package specification. You cannot use the literal null as a bind argument. So here, if you want to pass a null for the colon col 2 value, we cannot pass it as a null literal. Rather, we will have to declare a variable which is initialized to a null value by default and pass it as a bind argument. Let us see how we can execute a dynamic update statement. Let us say we have a procedure update record which takes in the table name as p table name, the column to be updated as p col 1 name, the update value for that column as p col 1 value. P where col is the column in the where condition and p where value is its value. So inside the execution section, we construct the update statement as execute immediate update concatenated with ptable name concatenated with set p call one name equal to colon p call one value, where p where call equal to colon p where value. Since colon p call one value and colon p where call are bind variables, we supply their values by the using clause using p call one value and p where value. We are concatenating the table name and column names and passing the values using bind variables. This one statement will construct the SQL and execute it also. The returning into clause is used for DML statements which return value using the returning clause. So as in this example, we have an update statement which after updating returns the account customer ID and account balance. So here we have declared L_item value as items.itemValue percentage type and given it a value of 100. L_account ID is accounts.account ID percentage type with a value of 1. L customer ID and L account balance will hold the return values from the update statement. Using execute immediate, we issue update account set account balance is equal to account balance minus colon p item value, where account ID is equal to colon p account ID, returning account customer ID account balance into colon L ID colon L balance. With the using clause, we supply the values for the bind variables L item value for colon p item value, L account ID for colon p account ID. The values returned are received using returning into clause. Colon L ID is received into L customer ID and colon L balance into L account balance. So the name of the bind arguments need not be the same as bind variables. We need to have a corresponding bind argument for each bind variable with the using clause and the return bind variables with the returning into clause. Instead of using the returning into clause, you could also receive the variables returned by the returning clause using out mode bind arguments as shown in this code snippet. Instead of returning into L cust ID, L account balance, you could do out L cust ID, out L account balance. But it is recommended to use the returning into clause. Let's see how to issue a dynamic delete statement. Here is a procedure delete table which takes in the table name to delete as a parameter pTableName. Inside the execution section, we issue execute immediate delete from concatenated with pTableName. This one-line command will construct and execute the delete statement. Using native dynamic SQL, we can also execute anonymous blocks. Let us see how we can use the in-out and the out mode for bind variables. For instance, here is a code snippet where we are trying to perform some calculation in an anonymous block. We have declared lSQL as varchar to 500. L_in_out is a number with a value of 1. L_in_out will be an in-out mode bind argument. L_out is a number with a value of 2. L_num is a number with a value of 1. Inside the execution section, we start constructing lSQL. We start with begin colon L_in_out equal to colon L_in_out plus colon L_num multiplied by 2. L_out, an out type of variable, is colon L_num divided by 2. This is followed by the end keyword, a semicolon, and the close quotation mark. Then there is another semicolon to end the lSQL statement. Now we say execute immediate lSQL using in-out L_in_out. So L_in_out variable is used in the in-out mode and its value will be passed in and the new value passed out. L_num is passed in the default in mode. L_out is in the out mode and its value would not be passed in, but the calculated value will be passed out and would overwrite its value. Also notice that for an anonymous block, you end it with a semicolon inside the string. We did not have to put the semicolon inside the string for other statement types. Secondly, for duplicate placeholders, for example the L_num bind variable, which is there 2 times, we just pass its value once. This is unlike other statements where we pass the same number of bind arguments as the bind variables, even though there might be a repetition. For anonymous blocks, we pass only distinct values in the right order. So colon L_in_out occurs first, so we pass it first in the mode we want. Colon L_in_out appears again, but we do not have to pass its value again. Next is the next distinct bind variable $lnum, for which we pass the bind argument lnum. Next is the next distinct argument lout, for which we pass the bind argument lout. Since we have already passed a bind argument for lnum earlier, we do not have to pass it again. A varchar2 PL/SQL variable can have a maximum length of 32K or 32,767 bytes. Prior to version 11G, the maximum length of string native dynamic SQL could parse was 64K by concatenating two varchar2s together, as shown in the first code snippet. However, starting with version 11G, native dynamic SQL can parse a glob which can hold up to 128 terabytes. So this length restriction is no longer there. In the second code snippet, we declare lSQL as a glob type and use it for the execute immediate statement. You can execute procedures in two ways, using the call statement or by using anonymous blocks. Let us say we have a procedure, calculate tier, which takes in three parameters: p_account_id in the default in mode of accounts.accountId% type, p_account_balance in the in-out mode of accounts.accountbalance% type, and p_tier in the out mode of type number. In the first code snippet, we use the call syntax to call the calculate tier procedure, passing in the three parameters as $accountId, $accountbalance, and $tier, and pass them in the respective modes with the using clause: laccountId in the in mode for the first parameter, laccountbalance in the in-out mode for the p_accountbalance, and ltier in the out mode for the p_tier parameter. It is important to pass the parameters in the right order and mode and compatible data types. The second way of executing it is by using the anonymous block with the execute immediate statement, which starts with the begin keyword. We then call calculate tier again, passing in the three bind variables and then ending it with the end and a semicolon. With the using keyword, we pass the three parameters in the right mode. We can execute functions using the anonymous block. Here is a function getTier, which takes in p_accountId in the in mode, p_accountbalance in the in-out mode, and p_tier in the out mode. So in the anonymous block, we declare laccountId, laccountbalance, ltier, and lout variables, and then using execute immediate, start the anonymous block with the begin keyword. We hold the value returned by calling the getTier function in $lout variable. We pass the three parameters as bind variables. With the using clause, we go from beginning to end, looking at distinct variable names. As with anonymous blocks, lout bind variable is mapped to lout variable in the out mode as it is a return value. Bind variable account ID is mapped to laccountId in the default in mode. Account balance bind variable is mapped to laccountbalance in the in-out mode, and bind variable tier is bound to ltier in the out mode. In this demo, we will see how to execute a DDL statement, a DML statement, and a procedure using dynamic SQL. We will also see the returning into clause in action. First, let's create a sequence, queue sequence, to insert the primary key QID in the orders queue table. Let us say we want to build a function which takes in the location from where the order originated, like Washington, California, etc., along with the account placing that order for the item ID for which the order was placed. We first declare a few variables, lcount, lid, and litemval, all numbers. We declare an exception no table exists, and then, using pragma exception init, map it to the error code -942. We then declare a cursor getItemVal to get the item value from the items table for the past item ID. Say in our system we want to create an orders queue table for each location, like orders queue CA for California, orders queue WA for Washington, etc. So if it is the first time receiving an order for a location, we create a table for that location also in our function. So that is happening in the first part of the execution section, where we try and take the count of rows from the table orders queue underscore appended with the past p location into lcount, This is enclosed in a block of its own so that in case the table does not exist, there will be an exception with error code -942 raised, which, using pragma exception init, we have mapped to no table exists exception. So if it is the first time an order is placed for a location, we create the table in the exception section using execute immediate create table orders queue underscore concatenated with p location and the columns QID, QAccount ID, and QItem ID. Having taken care of that, outside the block we issue a dynamic insert with execute immediate insert into orders queue underscore concatenated with p location to form the table name, its columns followed by the values as bind variables :PID, :PAccount, and :PItem with the returning clause returning QID into :LID. Now with the using clause, we supply the bind arguments qSequence.nextVal for QID, PAccount ID for :PAccount, and PItem ID for :PItem, returning into LID for :LID. We print the returned LID. Next, using the getItemVal cursor, we fetch the item value into LItem value for the PItem ID. Next, we use native dynamic SQL to call the process order procedure, passing in the parameters as bind variables and supplying their values using the bind arguments PAccount ID for :PAccount ID, PItem ID for :PItem ID, and LItem value for :PItem value. We return LID and end the function. Let's compile this. Now let's first see if the orders queue table for California exists. Select star from orders queue CA. No, it does not. Also, let's delete from the orders table and commit. Let's now run the generate order function for the location California for account ID 1 and item ID 1. It was executed successfully. Let's select from the orders queue CA table now. We see that the table was created and a row was inserted into it. Now, let's select from the orders table. Indeed, the order was placed for account ID 1. We can also use dynamic SQL for query optimization by passing in appropriate hints to aid the optimizer choose the right execution plan based on the information we know. For instance, here is a procedure apply fees which takes in a where column, p column, and its value, p value, and a hint, p hint. So we can append the hint to the select statement which is then executed using a ref cursor. In the next code snippet, we have an example of calling this procedure with PAccount ID column with a value of 1 and a hint to execute the query in parallel on accounts table with a degree of 3. The hint starts with a slash star and a plus and ends with a star and a slash. So in this way, we can override the default parallel degree for the accounts table. Only using dynamic SQL can you specify session control statements in PL SQL directly. So for instance, say we want to issue the command alter session set NLS date format equal to ddmonrrr inside a PL SQL procedure called set date format. We pass in the desired date format called pformat and then using execute immediate issue alter session set NLS date format equal to pformat concatenated. The way we call this procedure is as exec set date format and the format ddmonrrr. You might be noticing 3 quotes in the beginning and 3 at the end. Since we are trying to pass the string value as quote ddmonrrr quote, the first quote is for the start of the string literal. The next 2 quotes will translate to a single quote as the first quote will be the escape character. Similarly, the first 2 ending quotes will translate to a single quote and the last quote is to end the string literal. Using a combination of invokers write and dynamic SQL, you can create very generic centralized subprograms which can be called by any user and will act upon the schema of the calling user. For instance, the create table procedure which creates a table is defined as an invokers write with authID current user clause, and so it can be a generic procedure which can be called by any user to create a table in its own schema. Similarly, the delete table invokers write procedure uses dynamic SQL to delete data for the passed table in the invoker's user schema. You can use dynamic SQL to access programs or tables in remote databases using database links. For instance, say we have two database instances, DB2 and DB1. DB2 instance creates a database link, DB1 link, to connect to the demo schema in the DB1 instance. Then inside the delete table procedure, inside DB2 instance, it can delete data for the passed table name in the DB1 instance by using the DB link. The DB link is appended to the table name with an @ sign followed by the DB link name. One risk with dynamic SQL is SQL injection, which is the way a hacker can pass string input to an application to run malicious statements or get unauthorized access. One way is through statement modification. For instance, here is a procedure to delete an order for a given column and its value from the orders table. Inside, we build the LQuery string as delete from orders where p column is equal to p value, both p column and p value being concatenated. A normal execution would be, say, by calling delete order procedure with a column order account ID with a value of 1. This would translate to a statement delete from orders where order account ID is equal to 1 inside the procedure. But a malicious hacker can execute the procedure by passing order account ID and a value of 1 or 1 equal to 1. This will translate to a SQL statement delete from orders where order account ID is equal to 1 or 1 is equal to 1. Since 1 is always equal to 1, the OR condition will evaluate to true, which would lead to all orders being deleted and not just for account ID 1. This is an example of how a hacker might modify the statement and cause unintended deletes. The way to prevent these kind of attacks is to pass the value as a bind variable, which would also help improve performance. So if the procedure is rewritten to pass p value as a bind variable and supply its value with the using clause, the normal execution will be fine as before. But the malicious execution will error out with aura -01722 invalid number. The other way SQL injection can happen is through statement injection. This happens most often with dynamic anonymous block executions. So for instance, if we have a procedure called calc which takes in p condition, we then build an anonymous block in which we have an if clause concatenated with p condition concatenated with equal to a. Again, two quotes inside a string is a single quote, as one quote is the escape character. If it is true, we execute procedure proc1. Now a normal execution of this will be exec calc passing in a with quotes around it. This will build and execute a normal anonymous block where the condition will be compared as if a is equal to a. However, a malicious attacker may call this as exec calc 1 equal to 1, then delete from orders and if, and then start another if to continue the if in the anonymous block. So this will translate to if 1 equal to 1, then delete from orders, and if a equal to a, then proc1. So the delete from orders statement is injected by the string manipulation. The way to prevent these would be to have validations on the passed string and to check for occurrences of semicolon, end if clause, etc. Essentially anything which might not be normal. This would trap the error and raise it, preventing malicious execution. So incorporating validations on the passed string is always a good idea. Some other ways you might do to prevent SQL attacks is to be more explicit with date formats to prevent hackers from altering dates. These are some of the ways to reduce the risk of SQL injection in your code. In this demo, we will demonstrate SQL injection by way of statement modification. Let's create a procedure, delete orders, which allows us to specify the where clause using p column and its value p value passed in as parameters. We declare LQuery. Inside the execution section, we start constructing the query as delete from orders where p column concatenated is equal to p value also concatenated. Using dbms output.put line, we print the query. We then issue execute immediate L query to execute it. And then, using dbms output, print the rows deleted using the SQL %row count function. Let's compile this procedure. Let's first select from the orders table. There are currently two orders in it, one for account ID 1 and the other for account ID 2. Let's run the delete order procedure, passing in the where condition column order account ID having a value of 1. It forms the query as delete from orders where order account ID is equal to 1 and deleted one row. Let's roll back the delete. Now let's say a malicious user runs the procedure as delete order account ID with a value of 1 or 1 equal to 1. It translates to delete from orders where order account ID is equal to 1 or 1 is equal to 1, which will be always true. This causes both rows to be deleted. Let's roll back. Now let's see how we can prevent this injection. Let's modify the procedure to pass p value as a bind variable instead. Let's compile it. Let's execute the procedure with the malicious arguments again. This time it errors out. Let's run our normal execution now. It works fine with one row deleted. So using bind variables not only helps with performance but also helps prevent SQL modifications. In this module, we talked about dynamic SQL, which is SQL determined at runtime instead of compile time. The SQL is assembled at runtime based on user input parameters or processing logic. Dynamic SQL helps build extremely flexible and reusable program units. They have a variety of use cases like building dynamic queries with user-specified filters, dynamic sorts, running DDL statements, building frameworks and engines, just to name a few. Native dynamic SQL has a very simple syntax, and using the execute immediate command, you can easily run within your PL SQL code dynamic select, insert, delete, update statements, as well as DDL, session control statements, and anonymous blocks. Using dynamic SQL makes your code more vulnerable to SQL injection attacks. Using bind variables, validations, and explicit data type conversions are some ways you can minimize those risks. Hello and welcome to Pluralsight. My name is Pankaj Jain and welcome to this module on dynamic SQL using dbms_SQL package, which is an alternate way to execute dynamic SQL. It was the only way available to execute dynamic SQL until Oracle version 8. Oracle has upgraded this package with subsequent releases to handle collections, make it more secure, allow it to interoperate with native dynamic SQL with ref cursors, as well as to use it to return implicit results to the calling client from within a procedure. In this module, we will take a look at the various APIs available with this built-in Oracle package. We will understand how to execute dynamic queries, DML statements, DDL statements, and anonymous blocks with it, as well as to see how it can interoperate with native dynamic SQL. You need to know about the dbms_SQL package to maintain a lot of code in existing applications, as well as to use it for some tasks which can be only done using this package. So let's get started. So why should you use the dbms_SQL package? dbms_SQL can perform most of the dynamic SQL operations you can do using native dynamic SQL. Plus, there are certain tasks you can do only using this package. For instance, if you have an unknown number of select columns in a dynamic query, you can execute it only using this package. Similarly, if you have unknown number of placeholders or bind variables in your query or DML statements, which you do not know until runtime, then you have to use this package to execute such dynamic statements. Using native dynamic SQL, you have to know the number of input and output bind variables in the code while compiling them. With Oracle version 12c, the dbms_SQL package has been enhanced to return results of select statements to the calling client from within a stored program unit like a procedure, much like how T-SQL allows it. The dbms_SQL package is owned by the user sys, which is a super user. So naturally, this package is defined with invoker's right so that it runs under the privileged set of the invoker and not the sys user. The type of statements you can execute using the dbms_SQL package are DML, DDL, and alter session statements, queries, procedures and functions, and anonymous blocks. I should also add that the transaction control statements like commit and rollback can also be executed using this package. Let us look at some of the common steps when executing dynamic SQL using the dbms_SQL package. It provides APIs to call these different steps. You would start with opening a cursor. This step just allocates a context area in memory and returns a cursor ID. This cursor ID would be useful for all subsequent steps. The next step is to parse the dynamic SQL statement. This step checks the syntax and semantics of the statement, and in the case of queries, it also prepares an execution plan. The same cursor ID can be used for parsing multiple SQL statements. In case of DDL statements, the parsing step will also execute the DDL statement. Next is binding the input and output variables to the various placeholders in the SQL statement. The placeholders are identifiers in SQL statement with a colon in front, and through binding we associate it with a variable and tell the package its type and length. This is done only for the input and output variables and not for the columns in the select statement. For the columns in the select statement, we use the define column API to tell dbms_SQL the name and type of the variables which will be used to hold the values returned by the select columns of a query. So this step is needed only for query execution. Execute will execute the statement and will return the number of rows processed. Only in this step are the bind variables examined for type and size compatibility. Fetch rows step is again applicable only for queries where the next row in the results set is fetched in the variables defined with the define column step. This step will be called in a loop until there is nothing more to fetch. There is also an API execute and fetch for queries which will execute the query and fetch the first row in one call. Variable value step is used while calling procedures, anonymous blocks, or DML statements where values are returned in the bind variables. This step gets the output values. Column value step is used to get the values of the select columns for a query. The select columns we binded with the define column API. This step will be called after each fetch row call. Finally, we need to close the cursor to release the memory area. Not all these steps are required for executing the different kind of SQL statements. We will look at that and will also examine the APIs for these steps as we walk through the examples. Not all these steps are needed for executing DDL and session control statements. All you need are these steps. You open the cursor, parse the SQL statement. DDL and session control statements cannot have binds. Parsing the cursor also executes the DDL and session control statement. So the next step of execute is optional, but this behavior might change in future releases requiring an execute, so it is better to do an execute also. Close cursor would release the memory. Let's see how to execute a DDL statement and also understand some of the APIs of the dbms_SQL package in the process. Here is a procedure drop table to drop a table, the name passed in a ptable name parameter. We declare lSQL as a varchar to 100 to hold the query. lCursor ID is an integer, and inside the execution section, it holds the cursor ID returned by the dbms_SQL.openCursor call. So the first variant of the openCursor function takes no input parameter and returns an integer. Starting with Oracle version 11G, it has been enhanced to take in an additional integer parameter called security level to enhance the security and reduce the SQL injection attack risks. It has three values: 0, which has no extra security; 1, which requires that the user ID or role parsing the statement be the same as the one binding or executing it, or else Oracle will raise errors. 2 is the most secure setting, which requires in addition that the user ID or role binding, executing, defining, describing and fetching must be the same as the one which did the most recent parse. We will talk more about this security setting later when we talk about the security aspects of the dbms_SQL package. The next step is to parse the SQL statement. The parse procedure takes in the cursor ID obtained earlier with the openCursor call. Next is the SQL statement, and finally the language flag. The values for these are constants defined in the dbms_SQL package. V6 is for compatibility with Oracle version 6, primarily to handle the chars, as in Oracle version 6, chars used to be variable length character strings. V7 is for compatibility with version 7. Native, which is most commonly used, provides the behavior according to the database this procedure is running in. Foreign syntax is to specify that the SQL statement being parsed be translated according to the SQL profile in the database session. You would be using the language setting of native in most situations. Next is executing the DDL statement. The execute API takes in the cursor ID and returns an integer, which is the number of rows processed. The return value is valid only for insert, update, and delete statements, and for other types, it returns an undefined value. The execute step is optional for DDL statements, as the parse step executes the DDL, but that behavior might change in future releases, so it's always a good idea to also do the execute step for DDL statements. The close cursor step will close the cursor and will also release the area in memory. The close cursor procedure takes in the cursor ID to be closed. It is important to close the cursors to control the number of open cursors in the system and reduce any unnecessary memory utilization. Executing session control statements is similar to executing DDL statements. For instance, if you have to run the statement alter session set NLS date format equal to dd monrrr to change the date format in the session, then we can create a procedure called alter format, which takes in the format we want to specify, p format. We declare lSQL to hold the SQL, lCursorID and lReturn are integers. Inside the execution section, we build the SQL as alter session set NLS date format and concatenate it with the passed p format. We open the cursor and get the cursor ID, call the parse step passing in the cursor ID, the SQL, and dbms SQL.native language flag. We do an execute after that and then close the cursor. So you can run this procedure as exec alter format ddmonrrr. Two quotes inside the string literal quote will translate to a single quote, as the first quote will be used as an escape character. In this demo, we will see how to execute a DDL statement using the dbms_SQL package and see some of the subprograms of this package in action. Here is a procedure drop table which takes in p table name of varchar2, which is the name of the table we want to drop. We declare lSQL to hold the query, lCursorID to hold the cursor ID returned from the dbms_SQL package, and lReturn to hold the value returned by the dbms_SQL.execute function call. We start the execution section and build lSQL as drop table and concatenate it with p table name. Using dbms_SQL.openCursor, we open the cursor and obtain a cursor ID which we accept in lCursorID variable. Next, we do a parse call passing in the cursor ID, the SQL to parse, and the language flag of native. This parse call should also execute the DDL, but we still call the execute call passing in the cursor ID just so that if the behavior changes in the future And if it is the execute call which would actually run the DDL, we do not have to change our code. We then execute the close cursor procedure passing in the cursor ID. Let's first create a table called temp table which just has one column A, which is a number. Let's now describe the temp table to make sure it exists. Let's now call our exec drop table procedure to drop this table. Let's describe the temp table again. The table got dropped successfully and so does not exist anymore. Executing DML statements, subprograms, and anonymous blocks use the same steps. Only the following steps are needed. We need to open the cursor, parse it, bind any input or output variables if present, execute the statement. If we have any out kind of variables, as with returning values clause or as out parameters, we would use the variable value API to retrieve them. Finally, the close cursor will close the cursor. Let's talk about the bind variable API. This API, as I said earlier, is used to bind input and output variables to the placeholders in the SQL statement. It takes in the cursor ID as the first parameter, the name of the bind variable, which is the same name as the placeholder in the SQL statement, with or without the colon. The colon before is optional, but I like to put it just for read consistency. Then we can specify the value of the bind variable by tying it to a variable. So for a varchar2 bind variable, we can specify optionally a character set, and if it is an out type of variable, optionally the maximum size of the return value we expect. We will talk more about the size soon. This procedure is overloaded to accept number, date, glob, raw, etc. variable values. Let's see how to execute an insert statement using the dbms_SQL package. Here is a procedure insert record which takes in the table name, ptable name, and its two column names and their values, p_1 name and its value, p_1 value, p_2 name and its value, p_2 value. We have the same local variables lSQL, lCursorID, and lReturn. We build the insert string as insert into ptable name bracket p_1 name comma p_2 name bracket close, and then the values clause with the two bind variables :col1 value and :col2 value. We open the cursor and get lCursorID, parse the SQL, and then bind the two input variables. Each bind statement takes in the cursor ID, the name of the bind variable :col1 value, and associates it with p_1 value to provide the value and its data type. We do it similarly for :col2 value, associating it with p_2 value. We execute the cursor, print the lReturn value, which is the number of rows processed, and then close the cursor. Finally, we commit. Let's look at the variable value API, which is used to fetch the value of out type of bind variables. It takes in the cursor ID, the name of the bind variable, the same name we used in the bind variable API, and its value, which can be a varchar2 having an optional character set specification. This procedure is overloaded to accept number, date, glob, raw, etc. variable values. So let us take a look at an out kind of bind variable and getting its value using the variable value API. In a DML statement, using the returning into clause, we can retrieve extra information from the row or rows worked upon. So here is an anonymous block where we are trying to update an item value and then obtain the item name using the returning into clause. So it has litem value, litem ID, and litem name local variables, their data types based on the corresponding columns in the items table. We again declare lSQL, lCursorID, and lReturn local variables. Inside the execution section, we build the SQL as update items, set item value equal to :p_item_val, where item ID is equal to :p_item_ID, returning item name into :l_name. So here p_item_val and p item ID are input variables, and L name is an out kind of variable. We open the cursor, parse it for the SQL statement, and then bind the two input variables p item val to L item value, p item ID to L item ID. We bind the output bind variable L name to L item name, specifying the maximum length of the return value as 60. We execute the statement. Then using variable value, we retrieve the output L name bind variable in L item name. We print the rows processed and the L item name returned, and then close the cursor. So each output bind variable would be fetched using variable value call after the cursor execution. So as you notice that in this example, we specified the maximum out value length we expected for the L name bind variable. What if we did not specify the maximum length of the out variable as in the code snippet here, then Oracle tries to get it from the variable's initialized value. In this case, L item name is initialized to null, so it internally restricts the maximum length of the return value as 0. So if we try to run this block, then we will get an aura -6502 error for numeric or value error. The other way we could have passed the right maximum length is by initializing the output variable to the maximum possible length as shown over here. So now the bind variable statement will get the maximum length from the initialized value of the variable, and there should be no errors in execution. Let's see how we can execute subprograms using the dbms_SQL package. For procedures, we can use either the call statement or execute them using anonymous blocks. For function calls, we do have to use anonymous blocks. Let's look at the call statement for executing a procedure, and we will look at how to use anonymous blocks for function calls with the dbms_SQL package next. So here is a procedure called calculate tier, which takes in p account ID in the in mode of accounts.accountID percentage type, p account balance in the in out mode of accounts.account balance percentage type, and p tier in the out mode, which is the tier in which the account balance falls. Here is our anonymous block where we have declared L account ID and given it a value of 1. L account balance is accounts.account balance percentage type, and L tier is to hold the return tier value. We declare L SQL to hold the SQL, L cursor ID, and L return are integers. In the execution section, we build the SQL as call, calculate tier, and pass in the bind variables account ID, account balance, and tier. We open the cursor and get L cursor ID back. We then parse the cursor ID for the L SQL statement. The bind variable account ID is associated with L account ID variable, account balance is associated with L account balance, and tier with L tier variable. We execute the cursor. Using the variable value API, we retrieve the in-out variable account balance in L account balance variable, out variable tier in L tier variable, print those values, and then close the cursor. So using bind variables, we associate them and then get their out values using the variable value procedure. Let us see how to execute anonymous blocks using the dbms_SQL package, and also with that see how to execute a function inside it. We have rewritten getTier as a function this time. The parameters are the same in the in out, and out mode, and this function returns a number. So we start our anonymous block, which has L account ID of accounts.accountID percentage type, and assign it a value of 1. Then there is L account balance, L tier as before, and L out to accept the return value from the function call. We have L SQL, L cursor ID, and L return as integers. Inside the execution section, we build our L SQL string as begin :L out equal to getTier function call. L out is a placeholder to receive the value from the getTier function call. We pass in the 3 placeholders for the 3 function parameters. We end the anonymous block and put a semicolon before we close the quotes. For anonymous blocks, you need to include a semicolon inside the quote. We open the cursor and parse SQL using it. Then we bind the three placeholders to the bind arguments, laccount ID for account ID, laccount balance for account balance, ltier for tier, and finally we bind the value returned from the function lout to lout. We execute the cursor. For anonymous blocks, the value of L return is undefined, but we still need to receive it in a variable. Using variable value, we receive the out variables account balance into L account balance, tier in L tier, and the value returned from the function lout in lout variable. We print them and then close the cursor. So this is how you can execute an anonymous block and a function using the dbms_SQL package. Let us look at a demo to understand how to execute a function using anonymous blocks with the dbms_SQL package. We had created a getTier function previously which gets the tier in which the account balance falls for the past account ID. We declare laccount ID of accounts.accountID percentage type and give it a value of 1. Laccount balance is accounts.account balance percentage type. Ltier, lout are numbers. SQL is a varchar2. Lcursor ID and LReturn are both integers. We build SQL as an anonymous block with the begin keyword. Lout will accept the return status from the function, 1 for success and 0 for failure. GetTier function takes in account ID in the in mode, returns the account balance for this account in the in-out mode in account balance variable, and finally gets the out variable tier. We open the cursor, we parse SQL, we bind the variables account ID with laccount ID, the in-out parameter account balance with laccount balance. The out variable is bound to ltier and the value returned from the function lout is tied to the lout variable. We execute the anonymous block. Then we get the out and in-out values using the variable value clauses account balance in laccount balance, tier in ltier variable, and lout in lout variable. We print these values and then close the cursor. Let's run this block. The in-out parameter account balance gets a value of 1000. It falls in tier 3 and the value returned from the function lout is 1, which indicates success. Let us now see how we can execute select statements using the dbms_SQL package. As before for other statements, all the steps are not necessary. These are the typical steps for a select statement. We open the cursor, parse it, bind input and output placeholders to the bind arguments. For the columns in the select statement, we bind them to variables using the define column API. Using execute, we execute the select statement. The fetch rows call will fetch a row from the result set. Using column value procedure, we get the select column values in the variables we had associated with the define column API earlier. For a multi-row select, you would typically call the fetch rows and column value calls in a loop until fetch rows returns a 0. There is also an execute and fetch method which you can use to do the execute and fetch in one go. So this will save you a network round trip. The close cursor call will close the cursor. Let us look at the define column API. It is a procedure which takes in the cursor ID. The next parameter is the position of the column as a number starting with 1. So the first select column will have a position 1, second select column will have a position 2, and so on and so forth. Next is the local variable you want to attach to that column to receive the return value. Finally is the column size, which you would use in case of data types like varchar2, etc., which do not have a fixed length. This is a way for us to tell the dbms_SQL package the maximum length of the variable it should expect at runtime. The defined column has various overloads for accepting in columns of various data types like numbers, date, B file, binary double, etc. The column value procedure is used to retrieve the selected column values after the fetch call into the variables we had tied earlier with the define column API. It takes in the cursor ID as an integer, position of the column which is an integer, and the out value which can be a varchar2, date, number, etc. There are overloaded procedures for the various data types. There is another variant of the column value procedure which has the out column error parameter, which has the error code in case there was an error fetching for that column due to the value fetched, say when the actual length exceeds the specified length in the define column API. The next parameter of actual length gives the actual length of the selected column retrieved. This helps during the debugging process. The fetch rows function is a simple function which takes in the cursor ID and returns an integer, which is the rows actually fetched. If it returns a 0, this means there are no more rows to fetch. The execute and fetch function, as I had mentioned earlier, executes the cursor and also fetches the rows. So it is equivalent to calling execute first and then fetch rows. The second parameter, called exact, if set to true, will raise an exception if there are more than one rows fetched. It will still fetch the rows though. It has a default value of false where it will not raise any errors in case there are more than one rows fetched. So using this function can reduce an extra network round trip. Let us look at an example of a multi-row select to better understand the subprograms we talked about. Let us select the item ID and item name from the items table where item value is greater than a user specified value. Just to illustrate the mechanics of a multi-row select, I have created an anonymous block where I have declared litem_id, litem_name to hold the selected values, lValue to specify the value threshold for the where clause. We have our three variables lSQL, lCursorID, and lReturn. Inside the execution section, we build the SQL as select item ID, item name from items, where item value is greater than the p-value placeholder. We open the cursor, parse the SQL, then we bind the variable lValue to the p-value placeholder. We define the columns for the select. The first position for item ID tied to the litem_id variable, the second position for the item name to the litem_name variable. We specify the maximum expected length of item name fetched to be 100, which is how the item name field is defined in the items table. We execute this SQL statement. Inside the loop, we do a fetch rows call. If it returns a 0, meaning there is nothing more to fetch, we exit. From the fetched row, we get the selected values using the column value procedure, passing in the cursor ID. Position 1 to get the item ID in litem_id variable. Position 2 for item name in the litem_name variable. We print the values and end the loop. So in the loop, we keep calling fetch rows and the column value calls until fetch row returns 0 and then we exit. Finally, we close the cursor. If we accidentally fetch it in a different data type, for instance for position 1 for item ID which is a number, if we fetch it in litem_name which is a varchar2 variable, we will get an error aura-6562, type of out argument must match type of column or bind variable. dbmsSQL.lastErrorPosition function returns an integer which is the byte offset in the SQL statement where the error occurred. The first character is taken at position 0. So for instance, if there was an error in the SQL string syntax, it is very helpful to know the position of the error. So if you put a comma at the end of the item name, without the last error position function, the error we will get will be just missing expression. But with the last error position function, it will also tell us the position of the error, which is very useful for debugging purposes. In this demo, we will demonstrate the use of the dbms_SQL package to do a multi-row select. We will also see some of the possible errors we can encounter if we do not specify the right column type, for example, and see how we can locate the parse errors easily. So here is an anonymous block where we will do a select against the items table for items above a certain value. So we have declared litem_id and litem_name to hold the item information, LValue to specify the value threshold, LSQL will hold the SQL statement, LCursorID and LReturn are integers. LErrorPosition is to hold the error position. We build a SQL as select item ID, item name from items, where item value is greater than $p value. We open the cursor and obtain the cursor ID in LCursorID. We parse the LSQL. We bind the variable $p value to LValue variable. We then define the select columns and associate the column at position 1 with LItem ID and at position 2 with LItem name with a maximum length of 60. We then execute the cursor. Then in a loop, we call the dbms_SQL.fetchRows call, and if it returns a 0, we exit. Now we obtain the selected columns using the column value procedure, getting the column at position 1 in LItem ID, position 2 in LItem name. We print these values using dbms_output.putLine statement. We then end the loop and close the cursor. We have an exception section with the when others exception handler, where using the dbms_SQL.lastErrorPosition function, we get the last error position. In case of exceptions, we want to make sure that the cursor is closed, and so we have a close cursor call in the exception block also. Let's run this. We see in the output the item name and value of items above $50 value. Let us now see the last error position in action. Let us put an extra comma after the item name. Let's run this block again. We get the error aura -00936 missing expression at position 28. Position 28 is obtained by the last error position call, without which it would have been very difficult to locate where the syntax went wrong in the SQL string. Let us now demonstrate the error which will be raised if we fetch into the wrong data type. So let us fetch item ID at position 1, a number, into LItem name variable, which is a varchar 2. We get an error aura -06562, type of out argument must match type of column or bind variable at position 0. Let us correct it and bring it back to LItem ID as before. Now let us reduce the column length for position 2 for item name to say 5 characters. This is much lower than the value length in the column. We have declared two more variables, LColumnsError and LActualLength, both of type number. In the column value call, we have put in LColumnsError and LActualLength out parameters to get the error and actual length. Using the dbms_output.putLine, we are also printing these new out parameters. Let's run this block. We get an error code of 1406 with both and an actual length of 9 for one and 10 for the other. It however truncates the actual value while fetching it, making it 5 characters. Let us understand how the dbms_SQL package can help us with situations where there are unknown number of columns in the select statement or unknown number of bind variables in the where condition of the select statement. We will first take a look at some of the APIs which enable us to do that. The first is the describe columns API. It takes in the cursor ID as an integer. The second parameter is an out type called callCount, which is the count of columns in the select statement returned by the procedure. And the last parameter is again an out type called describe_t, which is an associative array declared in the dbms_SQL package. This associative array is a collection type, and each record in the collection describes a column in the select statement like its name, type, etc. The describe columns procedure is deprecated, and it is now replaced with describe columns 2, where the only difference is the out associative array type, which is of type describe tab 2. There is also a third procedure, describe columns 3, which has an out associative array of type describe tab 3. Let us understand these associative arrays a little better. The describe underscore tab is an associative array or collection object declared inside the dbms underscore SQL package. It is defined as type describe underscore tab is table of describe underscore rec indexed by binary integer. This is the syntax for declaring them, in which we are creating a type which is a table or a collection, and it is a collection each element of which is of type describe underscore rec. Describe underscore rec is a record, the definition of which we will see soon. This record contains various elements which describe the column, and we use index by binary integer clause to indicate that the index counter for the table or collection will be a binary integer. The only difference between the different describe underscore tab types is that describe underscore tab 2 is a collection of describe underscore rec2 type records. Describe underscore tab 3 is a collection, each element of which is of type describe underscore record 3 record. Let us understand the structure of describe underscore tab visually. It is a table or a collection containing several elements. The first element is accessed as describe underscore tab 1, and it will give us access to the describe underscore rec record stored at index 1. Similarly, describe underscore tab 2 will give us access to the describe underscore rec record at index 2, and so on and so forth. 1, 2, 3, etc. are binary integer index counters. Let us take a look at the structure of the describe underscore rec record. The describe underscore tab table has a collection of these record types. As I had mentioned earlier, for each select column, these hold the information like the column type, column maximum length, column name, the length of the name of the schema where the column resides, the schema name length, in case of numbers, the precision and scale of columns, in case of characters, the character set ID, column character set form, and whether this column is nullable. So a value of true would mean that null values are okay over here. So the describe underscore rec record type gives us a lot of information about the column in the select statement. Knowing the column type, for instance, can help us define the column and associate it with the right variable type. Describe underscore rec2, which constitutes the collection element for describe underscore tab 2 table type, has the column name defined as varchar2 32767 bytes, the maximum possible length for a varchar2, versus limiting the column length to 32 characters as with describe underscore rec record. So you should use describe underscore rec2 instead of describe underscore rec so that it does not error out if the column name happens to be more than 32 characters. Describe underscore rec3 has two additional elements for user-defined types. It has information on the column type name and the column type name length. So these fields are populated only when the column type is 109, which stands for user-defined types. Here are the different column types and their binary integer values, which you can use while working with describe underscore rec record type. When the number of columns in a select statement are unknown, then we have to use the dbms underscore SQL package. This is one of the unique advantages of using this package. Let us look at an example to understand the different data structures and procedures we talked about in order to find out the number of columns in a select statement and their information. Typically, these kind of subprograms can be used behind a search, say on a website, which allows the users to specify the information they want to see. So here is a procedure, describe columns, which takes in a user-specified query with unknown number of columns. We have declared L cursor ID and L number of columns, both integers. L describe underscore tab 2 is dbms SQL dot describe tab 2 type, and L describe record 2 is dbms underscore SQL dot describe record 2 type. Inside the execution section, we open the cursor, parse the query, then we call dbms SQL dot describe columns 2 procedure, passing in the cursor ID, L number of columns to hold the return column count from the procedure, and L describe underscore tab2 to hold the return table which has the column information. Then we open a loop, looping from 1 to L number of columns. We fetch the describe underscore rec at the index value I by using the notation L describe tab2 passing in the locator index. Now we can use the record to find out the column information like column name as L describe record2.column name, column type as L describe record2.column type, and so on and so forth. We end the loop and close the cursor. So for instance, say we call this procedure as exec describe columns, passing in pQuery as select order account ID, item name from orders items where order item ID is equal to item ID. Then the describe columns procedure correctly discovers the number of columns in the select statement and their types as evident from the output. So let us extend this procedure to also accept some user-defined bind variables. It takes in pQuery as before, but also a bind variable with a name pKey and its value pValue. I have just shown a single name value pair to illustrate the concept of working with bind variables in a query, but you can pass a collection of pname pValue pairs of all types your query takes like varchar2, date, number, etc. to work with unknown number of bind variables. So inside again we have L cursor ID, L return, and L number of columns as integers. We have the L describe underscore tab2 and L describe underscore record2 types. L number is a number variable, L date a date, and L varchar2 is a varchar2 variable. Inside the execution section, we open the cursor, parse a query, then call the describe columns2 procedure as in the example before, passing in the cursor ID and accepting the return column count in L number of columns and their information in L describe tab2 variable. Then in a loop, we describe the columns based on the information we received from the describe columns2 procedure. We run the loop from 1 to L number of columns. We get the describe underscore rec record at that index counter in L describe record2 variable. Say we are expecting just number, date, and varchar2 types in our select statement. We check the column type. If it is 2, which is a number type, we call define column and bind it to position I with L number variable. If column type is 12, which is date, we bind it with L date, or otherwise we just bind it with L varchar2 with maximum expected length of 100. This way we define all the columns in the loop. Next, we bind the variable pKey to pValue. If there were multiple key value pairs passed as collections, we could have just run this in a loop binding them over here. Then we execute the cursor and continue on. We will see a working example in the demo shortly. In this demo, we will demonstrate one of the advantages of using the dbms_SQL package, which is to execute a select with an unknown number of select columns. Let us start with seeing how we can discover the number of columns and their information using the dbms_SQL package. So here is a function describe columns which takes in pQuery, which is a varchar2, and pCursorID in the inout mode. The third parameter, pDescribe tab2, is of type dbms_SQL.describe tab2 is also passed in the inout mode. We declare L number of columns to hold the return number of columns. L describe record2 is a record of type dbms_SQL.describe record2. Inside the execution section, we open the cursor and hold the return cursor ID in pCursorID. We parse the input pQuery. We then call dbms_SQL.describe columns2 procedure, passing in the pCursorID and getting back the count of columns in L number of columns and their information in the inout variable pDescribe tab2. Now in a loop which goes from 1 to L number of columns, we get the record describing each column in the select statement. We use pDescribe tab2 and pass in the index counter I to access the record at that position and fetch it in pDescribe record2 record. Now we can get more information about that column by using pDescribe record2.column name to get the column name and pDescribe record2.column type to get the column type. You can of course get a lot more information using the other elements of the record. We then end the loop. Let's compile this function. Now let us execute this function in an anonymous block. We declare lCursorID as an integer, lDescribeTab2 as dbms_SQL.DescribeTab2 type, and then call DescribeColumns function passing in the query select order account ID, item name from orders items where order item ID is equal to item ID. lCursorID and lDescribeTab2 are the other two parameters being passed in. We hold the return information in L number of columns. Let's run this anonymous block. We see in the output that dbms_SQL was able to identify the column names and their types. Let's now extend this demo to demonstrate how to bind variables to the select statement and fetch the results. So here is a procedure, print results, which takes in the query pQuery, bind variable pKey, and its value pValue. Inside, we declare lCursorID, lReturn, and L number of columns as integers. lDescribeTab2 is of type dbms_SQL.DescribeTab2, and lDescribeRecord2 is of type dbms_SQL.DescribeRecord2. lNumber is a number, lDate a date, and lVarchar2 a varchar2 variable. We first call our function DescribeColumns, passing in pQuery, lCursorID, and lDescribeTab2. Now in the loop we define the columns. We go from 1 to L number of columns. From the lDescribeTab2 table at the index counter I, we fetch the record in lDescribeRecord2. Then we check the type of lDescribeRecord2.columnType. If it is 2, which stands for number, then we call dbms_SQL.defineColumn and tie the column at position I to L number. If it is 12 or date, then we tie it to L date, otherwise we tie it to L varchar2, as we are only expecting these three data types. You can certainly have more conditions for other data types. We then bind the input variable by calling dbms_SQL.bindVariableCall, binding pKey with pValue. We execute the cursor. Then, while dbms_SQL.fetchRowsCall does not return a 0, which would indicate no more data, we fetch the row. Again in a loop from 1 to L number of columns, we get the value of each selected column in the returned row with the dbms_SQL. Again, if the column type is 1, we get it in L varchar2. Column type is 2, we get it in L number, and for 12, we get it in L date variable. We also print the values using the dbms output statement. We then close the cursor. It is always a good practice to create procedures or functions which encapsulate a lot of dbms_SQL calls and which can be reused by different clients. This way, you don't have to write the lengthy code again and again. As well, you increase reusability, accuracy, and consistency in your code. Let's compile this procedure. Let us run this as exec print results, passing in the query select item ID, item name from items where item value is greater than :p_value, then pass the key :p_value and its value 100. From the output, we see the column name, the column type, as well as the fetched values. The dbms_SQL package has a lot of intelligent built-in security checks. One of them is the invalid cursor check. If an invalid cursor ID is used with this package, it will disable the dbms_SQL package for the entire session, and one would have to log out and log back in to work with the package again. This can greatly help avoid SQL injection risks. For instance, let us say that user demo is running a session with dynamic SQL. With the open cursor function, it obtains the cursor ID. Then later, somewhere down in the code, an exception is raised, making the execution flow to the exception block. The close cursor call never gets executed, leaving the cursor ID open. Let's say a hacker steals it and tries to run a malicious delete using it in another session. The execution will error out with aura -29471 DBMS SQL access denied. This would also happen if the user in his own session would have accidentally entered an invalid cursor ID to the DBMS_SQL subprograms. Every time the open cursor statement is called, it generates a random cursor number, making it difficult for hackers to guess. Also, there are some checks which can be performed with the DBMS_SQL package. These are controlled by the security level parameter we saw earlier with the open cursor function. 0 meaning no security checks, 1 meaning that the user ID role parsing be the same as the one binding or executing it, and 2 is the most secure setting. The checks which are performed are that the current calling user be the same as the one who did the most recent parse, that the enable role on current call be the same as the enable role for the most recent parse call, and also that the container on the current call be the same as the container on the most recent parse call. If any of these are not true, Oracle will raise the aura -29470 error for effective user ID or roles are not the same as when the cursor was parsed. Let us now see some security aspects of the DBMS_SQL package. Let us say that the describe columns function was compiled by user demo. This function is a definer's right function and would execute under the privilege set of user demo. User demo then grants the execute privileges on this procedure to user test. Now here is a session running as user test. User test creates a procedure print results in its own schema, and inside it, it refers to demo.describeColumns function. So now, since describeColumns function, which is a definer's right function, is executed under the privileged set of user demo, which opens and parses the DBMS_SQL cursor ID, then later, user test uses that same cursor ID for further subprogram calls. Oracle, in this case, would error out the execution. This is because the effective user ID and role using the cursor ID, which is user test, is not the same as when the cursor was parsed by user demo. Let's compile this procedure. Now in the test session, let's run the print results procedure again with the same parameters to confirm that. We get the error aura29470, effective user ID and roles are not the same as when the cursor was parsed. This is an important built-in security check in the DBMS_SQL package where it ensures that the effective user or role using the cursor ID is the same who did the most recent parse, and thus it helps avoid or minimize SQL injection attacks. Let us compare DBMS SQL versus native dynamic SQL, the two ways for executing dynamic SQL. Native dynamic SQL should be your preference for executing dynamic SQL as it is faster and easier and compact. For instance, in the top code snippet, we have an example of writing a dynamic procedure to drop a parse table name using DBMS SQL package, and in the bottom code snippet, we do it using native dynamic SQL. Notice with native dynamic SQL how compact and readable the code is. And here is a code snippet for a multi-row select using the DBMS_SQL package. And here is an equivalent piece of code doing it using native dynamic SQL. This further emphasizes the compactness and simplicity of using native dynamic SQL. So when should you be using the DBMS_SQL package? You should be using them for the tasks which only it can do, namely handling dynamic SQL when the number of select columns are unknown or when the number of bind placeholders are unknown. For all other situations, I would use native dynamic SQL. However, with Oracle 11g, there have been several enhancements to the DBMS_SQL package which allow interoperability between the DBMS_SQL package and native dynamic SQL. First is the addition of the DBMS_SQL.toRefCursor function, which takes in the cursor ID obtained by using the debugging_SQL.openCursor function, and it converts it to a ref cursor which can be used with native dynamic SQL. sys_ref cursor is a weakly typed ref cursor already provided in the database. So you might want to use it in a situation where the items selected from the select statement are known, but where it might be easy to use native dynamic SQL to fetch them, for instance in records, versus using several debugging_SQL.columnValue calls. So as in here, we are selecting star from items table where item_value is equal to :p item value. Since we have to fetch all columns of the items table, it is easier to use L items record, which is items %row type, to fetch them versus individual variables to hold them. So we first get the cursor ID using debugging_SQL.openCursor function. We parse it, bind the input variable to it. If there were an unknown number of bind variables, debugging_SQL would have come handy over there. We execute using debugging_SQL.execute function. After the executing step, we can now convert it to a ref cursor with the debugging_SQL.toRefCursor call, passing in L cursor ID. From this time on, L cursor ID no longer is valid and we cannot refer to it. We will have to work with L ref cursor from this point on. So in a loop, we fetch from L ref cursor into L items record and then close L ref cursor towards the end. Let us talk about the other situation where we want to utilize the strengths of the debugging_SQL package when using native dynamic SQL. This might be in the situation like where the number of columns are unknown in the SQL statement. We can use the toCursorNumber function in that case, which takes in the ref cursor in the in-out mode and returns an integer, which is the cursor ID, which can be used with the debugging_SQL package. The ref cursor has to be opened first before it can be passed in this function. This function can accept both strongly and weakly typed ref cursors. If you want to learn more about ref cursors, please refer to the Oracle PL/SQL Fundamentals Part 1 course on cursors. Once you have converted the ref cursor to a cursor ID, you cannot convert it back to ref cursor again using the toRefCursor function. So in this code snippet, we have a procedure getInfo which takes in pQuery with an unknown number of select columns. We have declared L cursor ID to hold the cursor ID to work with the debugging_SQL package. LRefCursor holds a reference to sys_refcursor. We again have lCallCount for the return column count, LDescribe tab2 table type, and LDescribe record to record type. We open the LRefCursor for pQuery. Now using debugging_SQL.toCursorNumber function, we pass in LRefCursor and convert it to L cursor ID. After that, we can work with debugging_SQL package using this cursor ID and describe columns using that. And from this point on, we also cannot refer to LRefCursor. We finally close L cursor ID using the debugging_SQL.closeCursor procedure. So we can run this procedure as exec getInfo, passing in a query with any number of select columns. In this module, we took a look at the debugging_SQL package used for executing dynamic SQL. We looked at the various steps involved in using this package for different statement types and along the way looked at its various procedures and functions. The main reason you would be using this package is when there is an unknown number of select columns or bind variables. Otherwise, for most other situations, you would use native dynamic SQL, which is faster, simpler to write, and compact. debugging_SQL has support for SQL data types as well as user-defined data types. It has been enhanced to be more secure in order to prevent SQL injection risks. It will make the package unusable for the session if an invalid cursor ID is passed, and has a lot of other checks available with the security setting parameter to prevent SQL injection attacks. Say for instance where it checks that the user parsing is the same as the one binding or executing it. Hi, welcome to Pluralsight. My name is Pankaj Jain and welcome to this module on debugging PL/SQL code. We all would agree on the importance of being able to quickly diagnose a problem once it occurs. Being able to write good performing code is equally important to being able to quickly troubleshoot problems. Oracle provides several tools and methods to debug PL/SQL code effectively in order to quickly provide bug fixes. We started our discussion on debugging PL/SQL code in Oracle PL/SQL Fundamentals Part 1 course, where we talked about several useful methods and techniques for debugging. We will build upon that knowledge and extend it to debugging stored program units. We will learn how to quickly find the place the problem is occurring, even if it is in a nested program unit buried several layers down in the call stack. We will utilize SQL Developer Debugger, a very powerful and easy to use debugger for drilling down to the root cause of a problem and doing a what-if analysis. So let us take a closer look at this extremely important topic. Some of the debugging methods we will be talking about in this course would be utilizing the putLine method of the DBMS output package. DBMS utility is another important built-in package provided by Oracle, which has some useful methods like format error stack and format error backtrace, which can provide us the information as to where in the call stack the error occurred. We will take an extensive look at SQL Developer Debugger, talk about what is needed to debug stored program units, setting breakpoints, and how to navigate the code to find problems quickly. We have talked about DBMS output and DBMS utility packages in detail in the Oracle PL/SQL Fundamentals Part 1 course, so I will just briefly touch upon them over here. We will continue to build upon the SQL Developer Debugger concepts we talked about in the Part 1 course and talk here specifically about debugging stored program units. The DBMS output package has several methods. We discussed a lot of them in the Part 1 course, but we will briefly talk about the putLine method over here. This method takes in a message parameter of type varchar2. The maximum length of the message you could pass in was 255 bytes for older versions of Oracle, which has been increased to 32,767 bytes for version 10.2 and above. The putLine procedure automatically puts an end-of-line marker after the passed message so that each message appears neatly in a separate line. So as shown in this code snippet, you could put different DBMS output.putLine messages throughout your code to observe values of variables or to know the current point of execution in the code. You would typically call it in the exception block to output error messages to the client console. One thing to note is that the messages will appear in the output console only after the block or program finishes executing. The output messages will not appear while the code is executing. That is where SQL Developer Debugger comes in handy, as it allows you to see the flow and interact with the code while it is executing. SQL Plus and SQL Developer are the tools where you would be using DBMS output the most. You have to enable the output and then call the getLine procedure to get each line. In SQL Plus, setting server output on will enable the output as well as call the getLine automatically for you. You can specify the buffer memory for the output fetches for the session using set server output on size 200,000 for example to set it to an explicit limit, or simply set it to unlimited. SQL Developer also allows you to set buffer size. We will see how to view output and set its size in SQL Developer in the demo shortly. Once set, it also performs enabling and fetching messages automatically for you. You would be mostly using DBMS output putLine calls for your unit testing. One drawback is that you have to keep modifying the code to add more lines in order to see more information. But on the other hand, it is an extremely easy way to debug. If the DBMS output is not enabled, then the messages would not show up in the console. So you could use enable and disable procedures to control seeing the output or not. And if you would further like to have more control, you could write your program unit such that it takes an input parameter, say pdebug, setting its default value to n, and then wrapping the DBMS output calls with an if check for this parameter. This way, you can control which messages you always want to see, say the ones in the exception block, but not be presented with the other debug messages until you are setting the pdebug parameter to yes. DBMS utility is a built-in package provided by Oracle, which has among others a couple of useful functions: DBMS utility.format error stack and the dbmsutility.formatError backtrace functions, which can provide useful debugging information. Both of these functions should be placed in the exception handler section of the code. The formatErrorStack function provides a formatted error stack. It provides information similar to the SQL ERRM function. The only difference is that it can provide information up to 2000 bytes, while the SQL ERRM function can provide only up to 512 bytes of information, and then it truncates the rest. So, this is a preferable function to use. FormatError backtrace function provides the line number information where the error occurred along the stack. For instance, in this code snippet, and I'm just showing partial code over here, say we have a procedure setLocation, which in turn calls a function getDepartment. Inside the getDepartment function, we have LID, a number, to which we try and assign a varchar2 string ABC. This would raise the numeric or value error, which will flow to the outer setLocation procedure. There, we have an exception handler section with a whenOthers handler where it would be caught. Here, calling the dbmsutility.formatErrorStack function will give us the SQL code aura-6502 with the error message PL/SQL numeric or value error, character to number conversion error. This is similar to the SQL ERRM function output, just that it allows for longer error messages. Calling the dbmsutility.formatError backtrace function and showing the return information with dbms output will give us the error stack and the line numbers of the error propagation. You should read it bottom to top. It says that the error occurred at line 4 of demo.setLocation procedure, demo here being the username owning these subprograms. Then in the stack, it occurred at demo.getDepartment function at line 6. So now you know the line numbers where the error occurred, as well as the propagation flow. Pretty useful information for debugging, especially when you expand this to several layers of call, as with most practical production applications. So you should include these function calls in your code in the exception handler section. Let us now take a look at a demo to see these functions in action. In this demo, we will see the dbmsoutput.putLine function as well as the dbmsutility.formatErrorStack and dbmsutility.formatError backtrace functions in action. Let us say we create a simple standalone function getItemValue which gets the item value for past pitemid of items.itemid %type. It declares litemValue to hold the fetched item value. Inside the execution section, we first put a dbmsoutput.putLine message entering getItemValue function with item ID concatenated with pitemid. Then we have a simple select which selects the item value into litemValue from the items table where item ID is equal to pitemid. Typically, you should obtain this using a cursor and then handle the situation if the item ID is not found. But here, to create errors for illustration purposes, I have written it as a select fetch. Then, using dbms output, we again put a message exiting getItemValue function. These messages can help us keep track of the execution flow, and you can put more messages in between to indicate other steps or values useful for your debugging. We finally return litemValue. Let's compile this function. Next, let us create a package called order management which just contains one function called getDiscount which takes in pitemid of items.itemid %type. This function would return back the discount we want to offer for an item based on its value. Let's compile this. Next is the package body with the implementation of this package. Again, we output a message entering order management.getDiscount function with an input item ID, pitemid, using dbmsoutput.putLine. Here, we first call the standalone function getItemValue, passing in pitemid to get its value, and then calculate LDiscount as 5% of its value. We then put a message using dbmsoutput.putLine exiting order management.getDiscount function with a discount concatenated with LDiscount. We return LDiscount. Then there is an exception block with the when others exception handler, we're using dbms output.putLine procedure. I'm showing the output returned by calling dbms utility.formatErrorStack and formatErrorBacktrace functions. I wanted to show you the exception call stack with different program units in play. Here, a packaged function calling a standalone function. Regardless of the program unit type, Oracle will show you the name and the line number in the error stack. Let's compile this package body now. Next is an anonymous block where we declare a local variable ldiscount of type number, and inside the execution section it holds the return discount value by calling the orderManagement.getDiscount function. First, let's call it with a valid item ID of 1. Before we execute this block, let's enable dbms output. If you do not have the dbms output window open, let's close ours for now. You can open it by going to View and then clicking on dbms output. Then you click on the plus sign and select your connection, in our case the demo connection, and click OK. This would enable dbms output in SQL Developer with a default buffer size of 20,000. You can change it to another value, or let's say we change it to unlimited. Let's first execute this block with a valid item ID of 1. From the output window, you can see the execution flow which we have indicated using dbms output messages. It says entering orderManagement.getDiscount function with an input item ID of 1. Then it enters the getItemValue function, which is called from within orderManagement.getDiscount function. Next, it exits getItemValue function and finally exits orderManagement.getDiscount function with a discount of 5. This shows how using dbms output.putLine calls we can debug the flow and put our messages to help with debugging. Now let's execute this block for an item ID of 3 which does not exist. This time it enters the orderManagement.getDiscount function with an input item ID of 3. Then it calls the getItemValue function and enters it with the item ID of 3. The select statement will raise no data found exception, which flows to the exception block of the orderManagement.getDiscount function. It is caught by the when others handler, where we see the dbms utility.formatErrorStack output of aura -01403 no data found. We also see the dbms utility.formatErrorBacktrace function's output. It shows the call stack as demo.orderManagementPackage at line 8, where it calls the demo.getItemValue function, and then the error occurs at demo.getItemValue at line 5. So this makes it very easy for us to debug and see what's going on and causing the error. Now let us explore the debugger tool of SQL Developer, which is a very easy and powerful way to debug PL/SQL code. Before we dive into a demo, I wanted to mention that in order to debug stored program units, you would have to compile them in the debug mode. Otherwise, you would not be able to set breakpoints or drill down into the code. Compiling it in the debug mode kind of opens the door to peek inside the code during debugging. Otherwise, without it, the door is closed and you cannot look inside. We covered the stored program units and the commands to compile them in the Oracle PL/SQL Fundamentals Part 2 course, but let me just give you the commands over here again. To compile a package HR Management in the debug mode, you can issue alter package HR Management compile debug. To compile a procedure test in the debug mode, you could issue alter procedure test compile debug. And to compile the getItemValue function in the debug mode, you could issue alter function getItemValue compile debug. Secondly, in order to launch a debug session from SQL Developer, a DBA user needs to grant some privileges. So say we want to allow the user demo to run debug sessions, in which case the DBA can grant debug connect session to demo and grant debug any procedure to demo. This would enable the demo user to launch a debugging session. In this demo, we will do a quick recap of the SQL Developer Debugger setup, look at various debugging views, as well as understand the navigation options. We will illustrate how to get to an error location quickly, along with being able to watch the flow and the variable values along the way to understand the execution logic and doing what-if analysis. Before we start, let's understand the pieces of code we will be using in our debugging demo. Here is a standalone function getItemValue which we looked at in the earlier demo. This function returns the item value for a passed item ID. Let's compile this in the debug mode. If the function is already compiled, you can compile it in the debug mode by issuing the command alter function getItemValue compile debug to compile it in the debug mode. We can also do it if we open up the function view, get to this function, right click, and choose compile for debug. Notice that the icon color changes to green, indicating that this function is compiled in the debug mode. Next is the package specification order management, which has a function getDiscount taking in p_item_id of items.itemId %type. It also has a procedure called print, which takes in p_message of type varchar2. Let's compile this. Next is the package body implementation, where we implement the function and the procedure. This is the same package body we had seen in the earlier demo with slight modifications. We have declared lItemValue, lDiscount, and initialized it with a value of 0, and lDiscount ratio, which is declared as a number. It first calls the getItemValue function, passing in the p_item_id. Then it applies a logic that if lItemValue is less than 600, then lDiscount is $10, and if the item value is greater than 600, then lDiscount is $20. Then it tries to find a discount ratio by dividing lItemValue by lDiscount. Then we have the dbms output.putLine message exiting order management.getDiscount function with a discount concatenated with lDiscount. It returns lDiscount. This is followed by the exception block. In the whenOthers exception handler, we print the error message using dbmsutility.formatErrorStack and dbmsutility.formatErrorBacktrace functions. The print procedure is a dummy procedure which just prints the passed message using dbmsoutput.putLine. Let's compile this package. Let us now recompile this in the debug mode by issuing alter package order management compile debug. We can also do it from the Object Explorer by expanding the package node and then clicking on the order management package, right-clicking, choosing compile for debug, and then we choose the package body and then also compile it for debug. You need to compile both the package specification and the package body in the debug mode in order to drill down inside it during the debugging session. Again, you would notice that the icon has turned green, indicating that these are compiled in the debug mode. Next, let's go to Tools, Preferences, and then click on the debugger. Let's check the Show Debug Actions on Main Debug menu to see the debug buttons on the main screen. In the Start Debugging options, let's leave it as the default Run Until a Breakpoint Occurs option. If you recall from Part 1 course, for debugging anonymous blocks, we had selected the Step Into option. Let's click OK and come out of it. Now let us grant our demo user the necessary privileges for it to start the debugging session. So we are logged in here as a DBA user and we issue grant debug connect session to demo and grant debug any procedure to demo to enable the demo user to start a debugging session. Let's run these commands. Having done the setup now, let us look at how to locate the line causing an exception quickly. We will run the order management.getDiscount function and pass it an invalid item ID of 3. Let's open the package body first. You can put a breakpoint by clicking on the left tab. This is the point where the execution will come to a halt. The red dot indicates that a breakpoint is currently set at this line, and you can again click it in order to remove it. Let's put our breakpoint again. There are several ways to start a debug session. You can right-click inside the package body anywhere and then choose Debug, or you could click on this red debug button over here, or you can go to the package, right-click and choose Debug. You can similarly start a debug session for a standalone procedure or a standalone function by right-clicking on the procedure or the function and choosing Debug. For the package, we can right-click on the specification or the body. It does not matter. It will open up a window for us, as we see here, creating an anonymous block for us to run the selected subprogram. Since we have two subprograms, it shows both of them as available options for us to run. Let's choose Get Discount. SQL Developer creates an anonymous block for us to run this function. Let us put an invalid item ID of 3 over here, and then let us click OK. Since in the debugger options we had chosen the option of run until a breakpoint occurs, it executes the anonymous block and then halts the execution at the first breakpoint. At this point, let us quickly recap the navigation options and debugging views. The first square red button is Terminate Debugging. Next, the red arrow is to find the current execution point in the flow. It will take you to where the current execution is at this point of time, which is currently at the first breakpoint. Next is the Step Over option, which will execute the current line and go to the next. If the current line is a function call, it will not go into it, but just execute it and go on to the next executable line after that. If, however, you have put in a breakpoint inside the function, then it will go there and stop. Next is the Step Into or F7 key, which will execute the current line like the Step Over option, but will drill down into the subprogram if the current line is a subprogram. Step Out leaves the current method and goes to the next statement. Step to the end of method will go to the last statement of the current method. Next is the Resume button, which will take the execution to the next breakpoint, and if it doesn't encounter any breakpoint, it will finish the execution. Pause will halt the execution but allows us to resume the execution again. Garbage Collect helps clear the cache of invalid objects. Now, let us take a look at some of the debugging views. First is the log window, where it gives you the messages for connection, etc. You will also see the messages from your dbms output.put line calls over here. Next is the breakpoints window, where it shows you the breakpoints currently in place. It shows you both the user-defined as well as the system-defined breakpoints. The first one is the Oracle exception breakpoint, which is a system-defined breakpoint which Oracle creates by default. Let's right-click on it and choose Edit. Let us check mark Break for caught exceptions. This will allow the execution to break even for caught exceptions. In the Conditions tab, we can define the conditions when the breakpoint should be evaluated. So if we define a condition which evaluates to false, the execution will not stop at this breakpoint. We will see an example of setting up a conditional breakpoint shortly. Next is the Actions tab. The default action is to halt the execution if it reaches the breakpoint. Let's click OK. For some reason, SQL Developer comes up with this warning: the class java.lang.exception could not be found. Are you sure the class name is correct? Just click yes to this. Next is our breakpoint, which we have established at line 8. Smart Data tab shows the variables Oracle thinks might be most relevant to you at the current point of execution. Data tab shows all the variables which we have declared so far and their current values. In the Watches tab, we can set up a watch for any particular variable we are interested in. Let's go to the Data tab and let's put a watch for the latom value. Let's right click, select watch, and now it shows up in the watch window. At this point of time, since our exception breakpoint is set and it is set to halt or break for both caught and uncaught exceptions, One quick way to find the line causing an exception is to hit resume at this point of time. If we hit resume, it will stop at the line causing the exception, or if there is no exception, it will just complete the execution. So let's just go ahead and click resume at this point of time. The execution stops at the select statement inside the getItemValue function, which is where an exception has occurred. So if we go to the data tab now, we see that the pItemID at this point has a value of 3 and an exception is raised. Let's expand the throw node. We can see the SQL code and SQL ERRM for the exception. So this is a very quick way to find the offending lines of code causing the exception and see the data values at that point of time. Let's click resume and finish the execution. In the log window, we can see the DBMS output messages from the exception block. As I had mentioned to you earlier that unless the execution completes, the DBMS output messages won't show up in the output window, one of the drawbacks of using DBMS output.putLine statements. In the next demo, we will see how we can navigate the flow of execution and observe the data values along the way. Having taken a look as to how to quickly find the location causing an exception, let us now see how we can navigate the code using breakpoints and go from one line to another to see the flow of logic and variable values. Let's go to Tools, Preferences, Debugger, and let us check the option of Step Into. This will make the execution stop at the first line of the anonymous block versus executing it until the first breakpoint. Let's click OK. Let's start the debugger session again. Let us choose Get Discount. This time, let us enter a valid item value of 2 and click OK. If you notice, now it has opened up a window with the anonymous block used to run the getDiscount function with the execution halted at the first line. Let us go to the order management package body. Let's remove the breakpoint we had put earlier. You can put breakpoints in the source code before starting the debugger session, or do it after starting the debugger session. Of course, your debugger has to be in the step into mode where it will stop at the first line of the anonymous block, allowing you to put more breakpoints. And while you are halted at one breakpoint, if you feel the need, you can put additional breakpoints in the code at that point of time. This time, let us go and put breakpoints, one at if LItemValue is less than 600 and the other at LDiscountRatio statement. Now in the breakpoint tab, we can see the pre-supplied exception breakpoint as well as our breakpoints at lines 10 and 15. Let us click on the exception breakpoint, right-click, edit, and make sure that the option Break for Caught Exception is checked. This would allow the debugger to halt for both caught and uncaught exceptions. Click OK, accept the warning, and click Yes. Let us click on the red arrow to find the current execution point, which as we know is sitting at the beginning of the anonymous block. Let us hit Step Over or F8. It will bring us to the begin statement. It will not stop at the variable declaration unless we are doing some initial assignment over there. Let us hit Step Over again and it will bring us to pItemID is equal to 2. Hit Step Over again and it will execute the expression and bring us to the line with the function call. If you go to Smart Data tab now, it will tell you the values of the two variables at this point of time. Since now we want to drill down, let us hit F7 or Step Into. If you would have hit Step Over or F8, it would have gone to the next breakpoint if it encountered one, or else it would have completed the function call and gone to the next statement. Now it takes us to the first line of the function call. Let us hit Step Into again and it stops at the LDiscount declaration where it is assigning it an initial value of 0. Hit Step Into and it takes us to the begin statement. Hit Step Into twice and it takes us to the getItemValue function call statement. Hit Step Into to drill down into the getItemValue function and it takes us inside the function. Notice that if we had not compiled this function in the debug mode, the debugger would not have been able to drill down into it. Now we can again hit F7 or F8 to go line by line, or just hit resume to go to the next breakpoint. Let's hit resume. It goes to the next breakpoint on the if L item value is less than 600 clause. Let us observe the value of L item value now. In the smart data or the data tab, it is 600. So this if clause would evaluate to false. Let's hit step into again. It goes to evaluate the else if statement. Let's hit step into again. It evaluates the else if clause also to be false. Let us observe the value of L discount in the data tab now. It is still 0 as initialized since it did not get assigned a value in the if or else if clause. Let us hit step into again. Let us look at the log window to observe how SQL developer is logging information. It has logged encountering the source breakpoints at lines 10 and 15. Let us hit another step into. We notice that now it has hit the exception breakpoint at line 15, meaning an exception has occurred at line 15. Let us go to the data tab. We observe an exception throws node. Let us expand it. We see the SQL code of 1476 and SQL ERRM of divisor is equal to 0 since L discount is in the denominator. Let us hit step into and the execution goes to the exception block. Let's hit step into, another step into, and now it is at the DBMS output statement. Let's hit another step into. Let us go to the log window. Even though it has completed DBMS output statement execution, we do not see the output in the log window because if you remember from our earlier discussion, the output of the DBMS output statements cannot be seen until the execution of the block or the subprogram completes. Let's hit resume. The execution completes and now in the log window we can see our DBMS output statements. So let us fix the logic by putting a less than equal to operator to cover the value 600 also. Let's compile the change again in the debug mode. In the next demo, I want to show you what happens to the navigation when the program unit is not compiled in the debug mode, how to set conditional breakpoints, and how to conduct a what-if analysis. We will see the effect of not compiling a program unit in the debug mode to the debugger navigation, how to conduct a what-if analysis, and conditional breakpoints in this demo. Let us compile the getItemValue function in the normal non-debug mode. You can see the icon color changes from green to gray again. Let us start a debug session in the order management package body for the getDiscount function. The item ID is 2, which is a valid item ID. Let's remove all breakpoints and just keep one breakpoint at the beginning of the getItemValue call in the order management.getDiscount function. Let us find our current execution point by hitting the red arrow. Let's hit resume. The execution flows until it encounters the breakpoint at the beginning of the getItemValue call. Let's hit step into or F7 to drill down in the function. What happened? This time it just executed the function and comes to the next executable statement. Since we have not compiled the function in the debug mode, it cannot penetrate into it. At this point, let's find the value of LItemValue in the data tab. It is 600 and hitting F7 or step into at this point will evaluate the first if clause to be true, assigning a discount of $10. Say as a part of our what-if analysis, we want to see the flow when the value is 601. Let's right click on LItemValue and do modify value. Let's make it 601 and click OK. Now let us hit step into again. So now the if clause evaluates to false and it goes to the else if clause. Hit step into again. Since we modified the LItemValue to 601, the else if clause of LItemValue greater than 600 is true, taking it inside the else if clause. Let's hit step into again. As we can see in the data tab, LDiscount is assigned a value of $20. Let's create a breakpoint at LDiscount ratio by clicking in the left tab. It gets added to the breakpoints in the breakpoint tab. Let's right click and edit. Let's go to the conditions tab. Here we can put in a condition without the where clause using the variables the session can see at this time. Let's put LDiscount equal to 0. So what we are saying is that stop at this breakpoint only if the value of LDiscount variable is 0. Since LDiscount is 20, the condition will be false and the debugger would not stop over here. Let's click OK. Let's hit resume. The debugger does not stop at the breakpoint at LDiscount ratio and the execution completes. This is how we can set conditional breakpoints. So in this demo, we saw the effects of not compiling a program unit in the debug mode, did a what-if analysis, and also created a conditional breakpoint and saw its effect. Knowing how to debug is an essential skill for any programming language. In this module, we talked about various ways to debug our PL SQL code. DBMS output is a built-in package with several subprograms available for debugging, like the DBMS output.putLine procedure. This is a very simple way to debug, but makes us modify our code to inject the DBMS output statements every time we need to add more debugging information. You can use this for small unit tests. DBMS utility is another useful built-in package. We talked about the format error stack function, which, like the SQL ERRM function, gives the error code an error message, but allows for longer message lengths of up to 2000 bytes. Format error backtrace is another important function of this package, which gives us the line numbers and the program unit names in the call stack propagation as the error occurs. You should put these calls in every exception block. Finally, we took an in-depth look at SQL Developer debugging capabilities in terms of setup, permissions, various debugging views, and navigating options. This is the most powerful and flexible way of debugging, and you should use this as your preferred debugging option.